So is there a way to
make that
this
look
window
better?
Yeah, because at the moment we're missing like half the screen or something.
I wonder if we go in and try and change the resolution of this. And that's out of range. So this is something that's a balance of the two, isn't it? How do we do that? That's best. Would it be possible to work with that smaller? Is that a bit
it makes
crap?
the workspace very tiny, so you don't get to see the data in a good way. And then also some things are hidden.
So, that's a bit of a pain, isn't it? Not sure what resolution would stretch. So we need something. Is that square? Why has that been the... No, that's side by side, isn't it? I guess the only other option is to do it off the...
Does it work if you use the extended desktop rather than the other?
But then that would be half the display, wouldn't it? Or do you mean...
No, if you
capture it.
But now that you'd see nothing on that one, if that's extended, because that's like thinking it's two monitors.
Yeah, you can make the projector the principal monitor, I think. I don't know if that would work with the recording.
Right. Possibly the best option then is to do it off your laptop, because then you get the full screen. This way, this monitor won't, that projector won't show a big enough screen, will it?
No, unless there are some other options, so it's just, I don't understand.
That
So
one
this
goes.
one didn't work. Okay.
So the resolution of that is fairly square, isn't it? That's kind of the problem.
You want to use?
So then,
better.
And then make that bigger.
This is a bit better. How do I get the other window of this one? Which one I use? I forgot. I forgot which option I use.
The first one in 4 digits is what 1024 we use.
This one?
1024, 7, 6, 8.
So you can go probably higher than that.
Yes, let's try.
Yeah, try that one.
This one and see. Hey, screw it up. That's good. And this one was not
Too high, I think.
This was not good. That's not good. Creo que I think the best one was this one.
Yeah.
Oh, which one I used before?
1024. The keep going. Sorry. The yeah. What was the yeah?
Which one?
Try that one. Yeah. One. Maybe the lower.
Here. Oh, the lower.
Yeah.
60 here. Maybe this could be the good one. Yay!
Cool.
Ready.
Sorry.
So
Can you see over that thing?
I can, yeah, when I can.
okay, so if you can put in your images.
Okay.
Maybe here I can pass my scale before I'm doing.
So the
Sorry, just I never use mine.
Yeah.
I don't know where to find the USB.
Go to the leftmost icon.
Here, Finder.
Yeah. Scroll down.
There, and then and set one is the just
Okay,
the
so
tracking.
can I move to desktop or something like this, or just copy?
Yeah, you should.
Or is there something where I can just...
The easiest way actually is if we just
Okay.
and then I'll copy that into the background while it's
Okay.
going. It's just going to take over for a minute.
I see, so one second.
There we go.
Okay, because otherwise it's
Yeah.
slow to run from a USB. Okay, so now desktop.
Scroll back up.
Oh, scroll back up.
Lower there.
Desktop.
So it's in set 1, and these are just a series of TIFF.
Okay,
images.
is all the same image? Or
No. So it's a time lapse. It's a 2D time lapse.
So these are the different times.
Yeah.
Okay. So when you have a TIFF image, you can just click the first one, and then you can go to settings and to see how the software is reading the numbering, because at the moment you see, for example, as a default is reading that this number is set, so we can change it 2 times, so it's being read in the good way. And press OK. And I'm going to use the option resampling open to see how big. Okay, it's not very big. It's 52 megabytes. So, okay. Okay, so from here, what are you interested in tracking? Because
So,
we have the bright
yeah.
objects.
No, so the bright objects, some of that's debris and some of them are dividing cells, but
Yes.
it's general the actual cells underneath there. If you increase the
Yes.
the contrast,
So if you click, okay, in PC is Control D. In Mac,
Edit display. Show display adjustment.
show display. Okay, so it's the funny symbol D. Okay. All right. So we can make now this a little bit more visible. These ones, yeah. So you're interested in tracking.
Yeah, the individual
these ones, but not the very bright ones.
So some of them are just static bits of debris that just sort of hang about.
Okay, and they don't move. Okay, but this moves. So
Yeah.
this is real cell, and this is no.
Yeah.
Okay, but that's okay because like this. Okay, but that's okay because we can differentiate them in terms of movement. Okay, are you interested in the shape or the volume, or is just mainly the
so
movement?
this was one of the things. We've tried doing the tracking just as a sort of centre of mass, but we just weren't sure whether there's kind of a better way, so we see it as a volume.
Okay, I think for this data set, it could be good to use a spot. The reason for this is because spots is very robust for object detection. I think you could use also surfaces because your objects, they are nicely in the screen. You don't see it very well, so I'm just going to saturate everything a bit because they're nicely individual objects. So we can try both. Perhaps I'm going to crop a little bit the data set to get rid of this front here, and also this front here.
Yeah.
The reason for this is because all these softwares, they are intensity based, so they are very good at picking up bright signal, and we don't want this in this case. So it's better if we remove it. So we can go to edit, we can go to crop CD, and basically I'm just going to crop the border. Like this. Okay. And now, for example, I can create a spot. The reason why I ask if the size is important is because obviously with the spots we make an approximation of the shape to a sphere. So we use total volume measurements, we use shape factor measurements, and if this is highly important for us, then we should create surfaces. But the advantage of a spot is that for big data sets, for very cloudy data sets, a spot is very, very robust for tracking. So I'll just go to the next step. And I need to establish the diameter of the object in the XY. In case that there are objects that they change dimension, here at the beginning of the creation wizard, you have the option of different spot sizes. So this means that if we have spots that they are growing in size, then we can allow for this. And if we select this option, then here we will enter one of the smallest sizes to let them grow. Because if we already input the large size, we will not make them smaller. So since I don't know, when it's the first time you analyze the data, you may not know what is the size, so you can go to a slice and you can pick up some of your cells. So obviously these images are not calibrated, so maybe this calibration can be a little bit strange. So 8.21 microns. So I can measure some other ones just with the left click of the mouse. So 7. Okay, 7.5. 8. Okay, so maybe I can choose an average of, I don't know, 7.5. So 7.5. I go to the next step. And now this threshold will allow me to start to pick up the object. So I need to move it to lower threshold values in order to pick up all the cells. Obviously, in these very large elongated objects, I will have multiple cells. That's also one of the limitations of this spot tool. But hopefully, I don't know if this one's moved, or because this could be multiple cells, and then I think at some point maybe they divide, or maybe not. Okay, I don't know. We'll see what we can do with them. But the important thing here is that these threshold settings that we set at the beginning of the movie, that they apply also in a good way towards the end, where we may have lower intensity conditions, if the sample photo bleaches.
How would you correct for that? You'd have to put that using XT to do a kind of a bleaching correction first and then bring it back in? Or?
No, also IMARIS, as a pre-processing option, you have, oh no, but it's an IMARIS XT function actually. As an IMARIS XT function, you have this option of normalized time point. And what this function does, which I think, is this the license of Sarah?
Yeah.
So she should have, I think she
that
bought...
MATLAB, she needs to install MATLAB though.
Yeah, probably it's not, because I think she bought this, but probably it's not active because she didn't install the MATLAB runtime compiler. But what this function, normalized time points, does is correct a little bit for the loss of signal along the time lapse. Yeah. In the meantime, that of course intensity is something that you don't want to follow over time, because otherwise you modify the intensity values, and if you see changes in intensity because it's something that is happening, some chemical process or some event happening, you correct for that, then the intensity values may not represent whatever you are seeing. Okay, so now I set up this threshold here, and I'm happy that most of the particles are detected. There may be some missing, but we have to, sometimes of course we have to make a compromise of detecting all the positive objects and detecting the least false positive objects. Okay, so now in the next step, this is a bit of a editing step. So if I have events like I don't know, like if I have detect a false positive, so let's say that, for example, this is a false positive there because, okay, it's not a false positive, but if there was very little signal, I could select it and delete it. Or, for example, if at some stage you can see an object that it has missed detection, like at this stage, I can do shift, left click, and create an object there. So it's very important, this shortcut here in IMARIS for the pointer between select and navigate. So if I press escape, I'm in the navigate mode, so that means that I can zoom out, I can pan, I can rotate the image. While if I'm in the select mode, that means that I can interact with objects. So I can select objects, or for example, if I move to a different time frame, if I'm missing objects here, if I'm in the select mode, I can also create objects pressing shift left click. And the size of the cube represents the size of the sphere. So it's at this stage where you can do some editing, because the better the object detection, that means that the better tracking you will do.
So the ones that you now added that it missed out, is it? So how is it going to track that if it missed it out in the first place? How's it going to know where?
Well, I just defined those that they were missing. I just defined it for a specific time frame, because maybe they were coming back at that next time frame because the signal maybe was coming up stronger, or so any editing that I do here is for a specific time frame.
Right.
So if something disappears for many frames, you are better off.
So if it's missing one time frame, how does it? So will it know that that was the one that was in a previous time frame?
Well, at the moment, because what happens at the moment, I'm just doing object detection. So I'm not doing any tracking.
Yeah. Right.
So I haven't linked one object to another yet.
Right,
that happens later. So at the moment, I'm just doing the detection of the object. So that's why if I detect an object here, and also it's non-existent at the next, so I'm better off if I try to also detect it there. Otherwise, they may not be connected, or there are certain, as we will see in the next step, there is a little bit of flexibility. So now I move to the next step. And this is where I get to choose the tracking algorithm. So this is definitely an autoregressive. Okay, each particle maybe is moving in a bit of a different direction, but they all have certain, they all have a directionality in their movement. Like for example, this one is moving down, so they have a directionality. It's not a random movement. So I choose autoregressive motion. And the maximum distance, this refers to the maximum step size of the object, the maximum distance that the object can cover from one time frame to the next one. So basically, it sort of represents a little bit this distance represents the radius of the circumference around which the algorithm will look for the object at the next time frame. So what happens here is that if we choose a maximum distance that is very large, let's say 50 microns, so what happens is that sphere is going to be huge, and the amount of particles that they are going to fall with those 50 microns, they're going to be many. So the chances are that maybe the algorithm may choose the wrong object to follow. If we choose it to something that is very small, I don't know, for example, 5 microns, what happens is that if the particle from time frame 1 to time frame 2, if it moves 7 microns, my tracks are going to appear very short. So I need to find a compromise, and I need to have a little bit of understanding what is this maximum distance. So for that, this grid is very useful. So if I go into frame, I can make the frame, so now the frame, this grid is 50 microns, so I can make it smaller. Let's make it 10 microns. And maybe in a spot, I can go, if I go into settings, I can choose the center point. So when I can see just the center of mass. So now I can see very clearly how much they move. So now it's easy, it's just a nice game to play, to just move from one frame to the next one and see how the particles move. Okay, so maybe they are moving, they don't move more than 10 microns. So okay, at least in this area. So let me go to a different area to make sure all the cells more or less behave in the same way. So they move Yeah, maybe they move within those 10 microns, even less than this. It looks like. Let me go to the end of the movie to make sure the movement is still similar, just because sometimes cells may speed up at the end of the movie or may slow down or okay, so I think 10 it can be a good starting point, a good guess. So I come back to create and I enter 10. Now the maximum gap size refers to the number of time frames that an object can escape detection. An object can escape detection because the signal decreases. Especially if we have a single plane, the particle can come slightly in and out of the focal plane very easily, and we can miss the spot we can miss the cell for 1 frame or 2 time frames. So the maximum gap size allows me for taking into account those events, and if I miss an object for, like for example, this one here, I think it's this one here. So now I have the object there. At the next time frame there, I miss it, and at the next frame it comes back. So that means that I can allow for a gap size of 1 frame, or just in case, I'm just gonna put a gap size of 2 frames. So this is more of a guess value and see what works for you. If your data set is very crowded and you think that whatever comes out of the field of view, I'm not sure if it's the same particle or not, you can set also a maximum gap size of 0. Yes, so 0 is also a value that you can enter there. Okay, so now I move to the next stage, and it's where all the tracks are being established. So normally, just to show you a quick tip, if I step back, if you set this value to something that is very large, you will find a lot of very straight lines. Okay, this is a very busy data set, but you will start seeing, here is difficult to see, but you will start seeing very straight lines. So if I quickly, maybe, if I do it here, you know what I mean. While if you choose something that it is too small, let's say 2 microns, the tracks will appear very short. So you will know, like for example, see here, all the tracks appear like very divided, so that's already an indication that probably your maximum distance is not good. So just to show you quickly. So here, if for example, if I choose a very large maximum distance, you start seeing this very straight line, which it should be a question mark for you, meaning that probably the tracking is gone wrong because your maximum distance is too large. Okay. So now what we have here is a filter, and this filter can help us to filter out tracks that we may not want. So for example, we do not want tracks for the objects that they don't travel, right? So therefore, we can choose a filter rather than for track duration. Okay, or maybe both. So filter for track duration will mean that we can exclude, for example, any trajectory that they last for a few frames or a few seconds. So let me see the calibration here. So okay, it's not calibrated. So 1 frame is 1 second, and we have 104 frames. So maybe we can exclude tracks that they last, let's say, less than 10 seconds. If I'm making any wrong assumptions, just let me know. So, for example, yeah. And then we can add a new filter to do with track duration, track length, because of course static objects can be there all the time, so it can be a track that lasts for the whole series, but they don't move. So as I move the threshold, you can see new trajectories appearing or disappearing. So then maybe you can set your own settings. I don't know what it will be best in this data set. But since the particles, they move around less than 10 microns per frame, okay, let's say the track length, let's exclude any track length shorter than, I don't know, maybe 5 microns. These are just some settings I'm using. You may want to adapt them to whatever you think is more correct, because this is for you to decide. For me, that I don't understand the biology behind this image. Okay, so that's it. There are no more blue arrows to follow. We can click the green arrow to finish. And now we can have the sphere back. Since this is a very crowded data set, of course, to see all the tracks displayed is a bit confusing. So maybe we can use a dragon tail. And the dragon tail, for example, displays 5, 6 time frames, the ones that you want. And when you play the movie, you can see that dragon tail. Okay, so this is how you will analyze your time lapse. You can also have the displacement arrow that shows the average movement of your particle or the directionality. You can make the arrow smaller, or you can hide it. You can decide to, for example, at the moment if I display all the tracks are time color coded. That means that a trajectory that starts blue and is finished red, that means that they last for most of the time series. But you can go into the color tab and say, okay, let's do something a bit more interesting. Let's color code the object in terms of a statistical value. And that statistical value can be, for example, a speed. So now, when you play the movie, so maybe I can use the blend mode if it helps to see, and the grid again, make it large because there are too many lines. Yeah, so that's there. So now when you play the movie, you can see your object, so it's very easy to distinguish if there are some fast events happening, because suddenly your particles will have a green or a red color if they speed up. This one is a slow one, so we could delete it or remove it if we want to. Or we can also color code not only the points but also the tracks in terms of a statistical value. And we can choose, for example, track length. So short tracks are in blue or purple, and long tracks that cover a long distance, are in red. And if you go into the statistics, of course you have all the statistics there. So you can go to, for example, See, you have two different types of statistics. You have the one for the spots or for the object. So, for example, speed. This means that they are statistics in a per frame basis. So, if I click at the speed, we can see the speed of the object for each time frame. Okay? But if you choose, for example, the option track speed, is not anymore a time-dependent statistic, because this is the mean speed of the object for the whole duration of the trajectory.
How do you export that data?
With these buttons. So with a single floppy disk, you will export only in this case, the track speed mean statistical value. So if I go to the desktop and I save it there.
Does that data give you any information about which sort of value represents which region on there as well?
What happens is that when you select an object here, it gets highlighted there.
Okay.
Or if you are in the select mode, you can select a track and the value is highlighted.
Okay.
If you click the multiple floppy disk, what happens is that all the statistical values are exported.
Right.
All the statistics.
Everything.
All the statistics.
Can you select a subset that you want to export?
So when all the statistics are exported, how do I minimize the window? I was saving it in the...
So save it to the right, that folder on the desktop.
Yeah,
to the right.
Pseudo 103 statistics.
You go to
Below
the
the
right
name.
end of the screen.
Oh, okay. Okay, I don't know what it does here. Okay, just I'm not familiar with how, but in PC. Sorry.
You can double click that.
When you export it, when you export all the statistics into Excel, each parameter it will be exported in a different tab within Excel. Yes, just that.
Okay.
If you want to do things like, for example, if you're not interested in, if you want to only a subgroup, then the best thing to do is for yourself to, you don't see it here, but here there is a little icon.
If you go up to the top where you click the yellow button, if you click the green one, so.
Oh, okay. Yeah. When you click this option here, you can configure the list of statistics that you want to calculate, because of course there are many, as you can see in this long list. Not all are selected. You may not need all, so the ones you don't need, you can deselect them and create your own list. So then when you export your statistics, only the ones that they are ticked and therefore that they are calculated are the ones that they are exported into Excel. And then you have also this little icon here that if, for example, if I have speed and if I select this object, I want this object here, and I click in this icon here, that means that the speed of the object is also plotted into my workspace. So you can see the value changing over time. And this can become quite handy when you want to create a movie and you want to highlight something happening. Okay. And then the same, it will have been done, or it can be done, if rather than to segment your object as a spot, you choose to segment your object as surfaces. It will be very similar process, but with the difference that with surface you get also information about volume and changes in shape.
So now you've identified the tracks and the centres, can you put an arbitrarily sized region of interest around each centre?
For which purpose?
So if you we've got time-lapse intensity, so fluorescence for cells, and we're just imaging the intensity, so it might be difficult to see cells, but what we'll see is a bright region grow, become intense, and then collapse. So if I don't think that the size tracking will work particularly well, what I can do is just draw a box around it that I'm confident the box captures the centre and calculate the intensity in the box.
So just for example to say how the intensity changes around a region of interest. Okay.
Exactly, yeah.
Yep. So then for that can be also easily done. So, for example, what we will do, since you will need a random shaped region of interest, then you can click in the surface, and does the region of interest change position or not? Just
yes, it tracks the centre of the cell. So these centres that you've extracted, I want to put a box around.
Oh, I see.
And the
what
box
you mean.
should move with the centre of the cell.
Basically,
Then no.
Basically, just trying to track the luminescence or fluorescence of the cell at the same time.
Then no. Then you depend on the signal. I see what you mean, because you mean like if my cell has a diameter of 10 microns, just look at the center of mass and draw a 10 micron spot. And you could try with a spot to see if that works.
And I can set the size. Can I fix the size of the cell? So I'll do it like that.
Yeah. Maybe the best thing is to.
So I'll fix the size of the cell.
You could do a spot.
Yeah.
And then you choose here a diameter, let's say of 30.
Yeah.
Okay. So now we're going to have something silly. And therefore, that spot will always detect the center of mass of the object.
Yeah.
So, of course, this is what you can do, because at the moment here is a quality factor. So this quality factor takes into account the signal and also the shape.
Okay.
So obviously, if I decrease it, it's difficult to pick up all the objects. So maybe we can choose, rather than a quality filter, we can choose an intensity filter. So it will be easier to pick up all the center of masses. So that's the only difference that you will do. The only thing that you will do differently.
Yeah. Well, the other thing we could try to do is to use the dynamic size allocation. And if we trust what that's giving us, then that will work equally well.
Sorry?
You mentioned a tab that was to dynamically...
Yeah, but that we don't have that function.
Oh, I thought I saw it.
No.
Aha, okay.
No. We don't have the function of let's say, of having this is the only thing that approximates, that you can establish any diameter you want in order to try to pick up the object, because we don't have let's say, a growing capability.
Yeah. And then when I go to statistics, that will give me the statistics within the
cell,
within the spot.
Within the whole area occupied by the sphere.
Yeah.
Yeah. So that will. So if you look at the mean intensity, it will be the mean intensity of all this area.
Yeah.
But wouldn't that make your intensities quite low if you've got a big area but a small high intensity?
Yeah. So we probably optimize it by eye, so that we know that it captures the whole of the cell when it's at its brightest.
Could you do it another way, that you have a second marker like the nucleus that you use as the seed point, and then do a donut?
It's loose.
All we've got is the separate. We have one slice building, which is the start, which is only really just a quick look at it. And then it's automated, so it will just take you the separate image every 20 minutes. And then it's sort of, it's bright at certain points,
You can
at
have a
other
look.
points it's
Can have a look at some data, can't we? It can be
Yeah, let's see if we have some time to help us out. Yeah, but it's very important that at least the center of mass always sort of remains, because if there is no signal, you can't detect it. Unless you add it manually.
So we've got these, we've got the gaps.
The maximum gap size, yeah.
They don't move that much. So.
Yeah, but then it's good, because then you can, because one dangerous thing of the maximum gap size is that if your particle, let's say they cover along, they jump a lot from one frame to another. If you choose that maximum gap size, a large value, then you have more chance, because in, let's say, 2 frames, for example, it can move 50 microns, then the chances is that probably is going to choose the wrong object. But if you hardly move, then you are in good, and your objects are nicely spread, you are in a good position.
I think
then we do that,
we can be reasonably selective and choose the ones that don't move so much as well. So that's not stress.
Come to worse, you also have some type of manual tracking. So if you, for example, select a spot, you can skip automatic creation, and you can choose this option, auto connect, to select the spot. And that means that you can select your object. So now you can select the diameter of your sphere to something, I don't know, large. And you can do shift click, you define your object, it moves to the next time frame, shift click, and you can.
Which is probably better than the.
Well, I'm using it.
I mean, it's a clicking option, but in case your object cannot be detected or
I'm using something similar to that at the moment, but the software is very good.
Yeah, so
even better than that.
And it also, if you want to exactly, if you have an object and you can exactly center to the center of mass, you detect it and you can say recenter. And it will slightly move the object to recenter with the center of, because you can click, but you may not be right in the center of mass, right? So you can just.
Can you make this sphere transparent?
Yes. So you can make the sphere. I mean, it's 2D, so maybe that's why, but you can make it transparent there. So it's in the color tab. And then you have there your, all your points, all your trajectories. And that will be a plan B.
Yeah.
Yeah, just in case.
Yeah.
Okay, good. Any other questions about tracking?
A little bit on the Vantage side.
Mm-hmm.
So when you've got all those tracks, just a couple of ways of presenting that data. I mean, one would be, so we get an idea of directionality. So whether we could recenter all the points to sort of a center point, and then be able to see if they all kind of moved in one direction, kind of.
Yeah, just have it on a circle. And
exactly.
Yeah, for that, unfortunately.
So that would be easy to do in MATLAB when you've got the Data Explorer.
Yeah, we do it in MATLAB.
Yeah.
We have a function for that in MATLAB, but because the compiler program is not installed here, so maybe I can show you more or less in here. This is a rubbish tracking. Let me do it again. So grab a chair, have a seat, feel comfortable.
We've done, haven't we? Yeah. Were you going to go into much more about the basic functionality? Or is that pretty much everything you were going to cover?
Well, probably there will be a lot more covered through the different sessions, because, for example, now we only cover tracking. There will be probably a lot more about image segmentation, or depending on the question.
It's tracking.
Yeah, it's just tracking.
But if this solves your problem, then it's cool.
So, yeah.
Feel free to come in and out or whatever.
Are you in, like, the chapter?
No, Nancy's Nancy's group, so yeah.
Excellent.
Alright, brilliant. If you need any help with the MATLAB side of it.
So maybe if you want, do you need to see that translation of tracks so they all depart from the same point or something? Okay, you are cool. Okay.
Yeah. Alright, thanks a lot.
You're welcome. So that function is when you go into the tab, in this last tab here. So here that you can see.
Right.
There is the function translate track. I think you have both of these, Sarah, but maybe the MATLAB compiler is not installed.
Probably, yeah.
That's why these functions are not active.
How do we install that?
I'll send you an email about it.
Yeah, because I would like to install it. We
Yes.
are going to have a mathematician with that.
Oh, so you will use it.
Yeah.
Yeah, definitely. So then the idea is that you just select a track, and then you click in Translate Tracks. And so now that you see, that starts the MATLAB compiler. MATLAB is not, you don't need it in the computer to run. It's just a compiler, which is free to download. And that translates track. So this means that now, when I play the movie, they all start from the same point, and then you can see that directionality. And then
that's through Z as well.
Yes, of course. Yes. And then you can go and plot this in Vantage, because you have your normal spot, but maybe we don't want the normal spot. We want the translated spot. And this is much better plot than just the one that shows only X, Y dimensions. Okay, if you only have a 2D, then doesn't matter. But if you have a 3D, then this also reflects the Z direction. And then you can choose not only position, but also some other additional parameters. So now, for example, we can have X, Y dimension, and maybe, I don't know, the scale can be intensity, the intensity of the object, and the color can be the speed of the object. So that means that when you play the plot, if the spot becomes big, that means that it becomes brighter, the intensity increases, and if the spot becomes brighter, like blue or like green or red, that means that it moves faster. And you can make a movie of this. So you can do many things. You can have the plot just showing the spots at each time frame, or you also have the option of showing all the objects for all the frames. So then when you play the movie, nothing happens, because you have all the objects there. And then maybe you just want to, I don't know, create a snapshot or I don't know, whatever. Cool. Yeah?
Yep.
Happy? Good. Do you want me to save this data set?
No, it's fine.
Yep, okay, cool.
That's the one that was Brightfield.
This is the one that it was the red signal. I don't know if this was Brightfield or...
No, that's what I mean. This is the algorithm.
That converted the cells
into
into
pseudofluorescence.
Nice. Yes, nice. Cool. Okay. So, let me close all this thing. Okay. So shall we look at some of your data points?
Yeah, so they're in that, you see that folder there? Down at the bottom, yeah.
Okay, excellent. Okay, so let's open
Maybe
IMARIS.
the mitotic spindle copy.
Okay. This one, yeah. And
This sort of one down, that one. No, sorry, this one.
this one. Okay, so let's go first to the sampling open, just to see a little bit the size because
It's quite big, but it does open okay, actually.
okay. Okay. So okay, so we see that the analysis it runs a bit slow, so
Yeah.
we will
I
drop it.
just kind of wanted to show you what we've done so far.
Yes.
Really help us improve it.
Cool.
But if you go to the animation, you can see what we've done. Running the animation through.
Okay. So you run through that. Yeah, you see all the projection. Nice. And then you've done some rendering, some segmentation. Very nice. Yeah, to see the mitotic spindle. Very nice.
So
Yeah.
this is where we have the trouble with that zoom in.
It zooms back.
Yeah, where it zoomed back and when it gets in here, it was doing like a double zoom, but so the support got back to us and
Yes.
suggested the doing double image from the same place and overlaying them,
Yes.
which is also what we
When we play it in there.
Okay. Okay, yeah, because I didn't know that, for example. So yeah. Okay, that's
But
nice.
so what we do like some help with
Yes.
is reconstruction. So we're reconstructing the centriole, which is those reds.
Yes.
But they kind of end up looking a bit kind of wobbly and bumpy. So whether you might be able to
Too small.
do a
Okay.
job.
Oh, okay. You done a very good job, Sarah. Oh, I don't know who did it, but
Me
you
and
did it.
Laura combined.
Yes, it's nice. It looks very nice and moving. Very nice. Very nice.
I don't need to help you anymore. Can I just go now?
It's
Very nice.
long time
Yeah,
to
I
do that.
could-
Yes, and
Yeah, but it makes your talks easy when all you do is play this movie.
Yeah, just play it.
yes, and
I'll talk again in 10 minutes.
images are not easy to segment, so.
Yeah, and if you've got any suggestions for the animation.
Sometimes it's just one tip why maybe the centriole may look a bit.
Mm.
And when you do when you create a surface and skip automatic creation, so for example, I don't know, you are even able to see the centrioles. I cannot even, I don't know where they are,
Yeah,
but
keep going through.
Keep going,
Yeah.
okay.
Keep going.
Yeah.
Yeah, it's there. If you zoom in on the
Oh,
right-hand side,
here.
Yeah.
Okay, yeah, that little bin. Yeah. Okay. So when you, I think what Sarah has been already doing in a very nice way, when you try to do this, to use these contour tools, as you can see, I have turned off the volume, because if you have the volume on, you just see the whole block of signal, and it doesn't help. So you have to turn off the volume, so you just see the signal projected in that specific plane. And when you draw in mode, you have the different drawing modes. So normally I find this one, the ISO line, quite handy. if what happens is that you're looking at smaller structure, you want a little bit more resolution, you can increase the density. And this density basically means, to start drawing.
So the
So
central,
that's, yeah, it's not quite there.
yeah,
So if you go up and down through the position, oh, okay. You can't follow me. I can't work out on here. It's easier to see up there.
Sorry, you can move, you can take control and show me where it is.
Okay, so we need to zoom. Oh. How do you move it across?
Just with a right click.
Okay. And then so they are there.
Oh, okay.
So this is one sort of yeah, I can't move really slow enough. It's sort of here. But
Okay,
that's why they
I see
look
the area,
really-
yes.
We wondered if we could put a sort of false shape,
It's
like
something,
a cylinder or something.
like a cylinder, yeah.
Which we've done in other programs.
Yes.
Can we do that?
Yeah.
Can you show us how to do
yeah.
that?
So
Sort of based around where it is,
this tool adds a circle.
right?
So there are two tricks with EM. One is to invert the image depending on what you want to see.
Right.
So sometimes, I don't know if in this case, rather than to see all this bright, to see this bright, maybe it could help. So something that you can do is edit. I'll just show you where the function here, where the function is, or for image processing, contrast change, invert, and this inverts the grayscale. So it can help you depending what structures you want to segment, maybe to help you visualizing.
Yeah, I'm gonna try.
And also, so for example, if in here you just want to build a cylinder-like structure, so I go to select when I want to start drawing, and then I click in the draw button, and this option here adds a circle. So I can see now. So maybe let's see if I can make it in a different color, maybe red. So this circle, with the wheel of the mouse, you can make it the size that you want. And when you are happy, you can just click in order to create the circle. Obviously now, for example, it has very little number of vertices, so maybe I can go to edit, undo, and maybe increase, because the more vertices, the more detail. So I can say 30.
So is it only going to ever be able to do a cylinder that way, or can we turn?
Yes,
Up? 'Cause the way the centrioles are is they're like that. So we want one, if they're perfectly lined up, we want one cylinder going that way, one going the other way.
Okay,
That.
so then,
So can you just keep showing it? 'Cause
yes.
We don't know how to do anything.
So then with Control minus, I just make the vertex smaller. So then the idea will be, if this one goes in at the moment we are in the XY direction. So if this one is okay in the XY direction, we define it like this. So then you can, oops, I lost it. You can go to different planes and keep on adding the cylinder. Now look. Sometimes if it helps you, you can also enter, if it goes too fast, the plane manually, if it jumps too much. So for example here I lost it, so Maybe let's go to 6, 9. Let's say here, fitting thinner, and then I'm just going to the different plane. Oh, to 59. If the contours are in the way, so visibility none, and you can hide them. So I don't know. Okay, let's say I don't know if it's just over this frame. So you can. Sometimes what happens is that you may need to use a manual resolution, and you can increase it to the maximum to get the most resolution when you create the surface, especially when they are very small objects, and create surface. So then you create that cylinder type of surface. And then if the other structure is in the X set or in the Y set dimension, you can change the orientation of the plane depending on what it helps you to better.
Choose an arbitrary plane. An arbitrary angle.
No, it's always flat plane in any of the 3 dimensions, but just flat plane. Because if it's arbitrary plane, then you're just better off to draw plane by plane. So maybe if so basically that's the little the little structure that we have there.
So you're saying with the isoline selection, so is it the lower the, what does the percentage mean exactly?
Yeah, so here if we get to use, for example, in mode the isoline, this density refers to the number of voxels, of vertices that you want when you create a contour. So the higher the density, the more vertices, and therefore the more detail that contour has. And the isoline, so maybe the isoline works very well, of course, for structures, for example, like this one. So you can detect that structure. For your centriole, it may not work so well, but for these kind of structures,
yeah, that's what I use this for the chromosome.
Yeah. So therefore, if you select that and you think this does not have enough resolution for me, you want something, especially if it's a very small object or something, you can increase the density. Of course, the more density, the heavier will be that image. And you see now we have more dots. So control minus, so if I reduce, so now we have more of these vertices that form the contour, so therefore a much smoother line as opposed to, for example, now if I choose maybe just 5, and if I draw a contour here, see, the density is less, therefore less vertices and more like kind of straight lines.
It doesn't make any difference to how it's selecting where it's
No,
drawing the line.
because selecting is based in intensity.
Right.
Or in this case, it's based on the signal. So it tries to detect all, for example, here, if I put my mouse here, it's trying to detect sort of all the pixels that have same intensity value or similar intensity value.
So is there a way, if you've got quite a weak, something that's not that different from the background, to make it easier to select it? So like by eye, you can see
you can try, like for example here, I don't know, you can try the isoline. Normally this is the one that it will give you the best result to see if it can detect small changes, see if it works.
So how does it, there must be a setting of what level of difference.
Yeah, so wherever you place your mouse, it takes that intensity value and it tries to trace a line through pixels that they have same intensity value.
Right. But there must be a variation. So you change that variation. If you've got something really dark, it's going to be different to something that's quite close to the background.
Yes, but that's set by where your mouse is sitting. So
it's like a sort of sensitivity thing, isn't it? But
so now, for example, if I'm here, it's detecting just a very dark one, or even here, see, I'm detecting the double membrane there. But if I'm a little bit towards a bit more to the lighter one, so it doesn't detect the double membrane anymore.
But there's no thing that you can change, say, like I want to select plus or minus 5 grey values.
No.
Around.
No. No, so yeah, those are normally this one is very bad for EM because it takes a long time to calculate, because it will try to select, this is local, this, it will be for the whole thing, so it's not very practical for EM, the magic one. The circle adds a circle like I show earlier, and then you have this other drawing mode, like the distance one. So the distance means that in this case, every 6,305 microns, a dot is added. So of course,
isn't there scale on this one?
these images are not calibrated. So if you want, you can, before doing anything, you can go to IMARIS, to source file, where is here, edit image properties and enter the right calibration. Yeah.
That's an angstrom.
Yeah.
The numbers
Yeah. So that's,
No, we weren't taking those numbers as being right.
Oh, they are right. They're in angstrom.
Right. So I can see
They're
they
at 16.8.
okay.
Okay. I'd assume they weren't.
So then you just need to change
they're in
image properties and
it's 16.8 nanometers by 100 by 16.8 by 100.
so edit.
So this read the
Did
preview
you know
file.
that?
Yeah.
I think
I guess you have thought to.
yeah, because we decided it.
Yeah.
The file header has it in angstrom because it's a tomography software that I use, which angstrom is the
Okay.
default.
I don't know here, but in PC version, when you open the image properties, it's not there anymore. Because we used to have a button here that it says microns or nanometers. Okay, I don't know if we get down to angstroms.
You just put points in the 16.8. I mean, you could divide them all by whatever it is to get into my
So, for example, here you can enter a separation between the vertices. So you can get, again, more resolution, so you can set it up to, I don't know, 2000. And then when you try to draw every 2000 units, it adds a vertex. So the smaller the space, again, the more definition in your contour, so equivalent to this density here. And then you have this other drawing mode, which is equivalent, but rather than to be, this one is distance, and this one is time. So if I undo my previous contour, That means that I can say, okay, add a vertex every 300 milliseconds. So you do a single click, and every 300 milliseconds you have a vertex. So again, you can have again a nice, you can control the resolution of your contour. I think then join the dots. And this one is the classical one, which every time you want a vertex, you click. And then it can be widely spread or closely spread. Does it make sense? Mm-hmm.
I quite like the timed one. That using that. I think that
The timed one is very good.
it's really easy, whereas I think sometimes when you do the one where you press, it makes it less smooth as you press.
Mm-hmm. And it's more tedious to be all the time
You go
clicking.
through and do this on every slide through which you have your object.
Again,
Your
yeah, again, depending the higher the resolution or the higher the details you want in the surface, the more you have to draw it in the different planes.
so
So
it's only about 3 planes.
yes, but then
For the centriole I was drawing
Everyone.
For the chromosomes, I
No.
think I was drawing every 5 in the end. And if you
Okay.
did it more than that, it started to look kind of false.
yeah.
It just makes up in between.
Okay.
Yeah, because you can, so for example, if you draw in plane 1 and you draw in plane 10, then the software tries to
Okay.
made up.
Usually, if we want a cylinder, we probably want to draw in less.
Yeah.
You can, yeah, if you wanted a plane, yeah,
Do a circle at the top and the bottom.
yeah, and we join them, yeah, exactly,
It's straightforward.
yeah. Cool. Any questions about how to draw or use the contour tool?
Not for me, but I don't know if other people do it more.
Because this applies for also for when you are working with fluorescent images and the creation wizard doesn't work because, I don't know, maybe the signal to noise ratio is very bad, or sometimes you can use this contour tool to draw a random shape region of interest. So your raw, it can be, you can draw by hand any shape, and you can say, this is my ROI. And then you can go to board, you can copy, and then you can go to the bottom, and you can oh no, this is, sorry.
I have sort of one
yes.
more question. Before I forget.
Yeah.
How do you change the size of those the dots?
Control minus or control plus.
Okay.
So control minus makes it smaller, control plus. Also, any question, right click, show help, and you see contour. You can click in contour, and where it is, there are the shortcuts, because with the contour tool there are quite a lot of shortcuts. So actually, I think search, maybe if I click shortcuts overview, and these are all the shortcuts for the contours, because you can also move a single vertex, you can translate a whole contour, plus minus to decrease or increase the line, and probably these are easy, and they are all mapped or the same. I can't remember anymore. Yeah, so you got your shortcuts there. And what I was saying before is that board paste, so in case you want to paste a contour or something. Because sometimes this can help you to draw random region of interest, and something that can be useful for EM, maybe to save you some, maybe, I don't know, if in some cases can help some manual drawing, is to imagine you have this structure and you want the detail that is inside, so something can happen, I don't know, inside the cell or something like this. So you can draw a random shape around here and create, maybe I can show you in a different data set. So I close the file, so there is nothing done to your nice image.
So I copied it. Just in
Oh, yes, again, okay. Yes, because that has a lot of work. That has a lot of work. So, is this, where are the program files or something like this, application? Maybe not here. I'm trying to look for the bitplane folder. Do you know where it could be?
If you go into applications, that was date modified. If you change it, click on the name at the top.
Ah, here.
Wait,
Ah, okay, well. Bitplane IMARIS. Fine. Oh, I can't find it. So no.
If you go to Mac hard drive, and then go into applications, and then click on the name at the top, so that
so it's all alphabetically. So no, it's not here.
It might be under I. There it is.
No, but this is the executable file.
If you right click them, they're quite often folders these days.
Oh, really? Okay, sorry.
No, not that.
Ah. Sorry, you can see. Yes.
Yeah, if you click that.
Oh,
It's a new thing with the mouse, they kind of hide all the content.
oh.
So it's executable. So if you double click it, it starts the program, otherwise the content's inside.
Oh, okay, see, okay, so not here.
Some sort of idiot proofing.
Yeah, they just work.
Look for nice symbols and that's what you want.
Yeah, you can't find things to mess around.
Okay, no, I can see, but anyway.
Resources?
Resources, I'm lost in Mac. Colors, okay, in share support. Okay, now. So if you go to that share support, first, in XC, you will find all those MATLAB plugins in case the mathematician wants to open the MATLAB program and change it somehow and do something else, and so that's where the programs are. Then in images, you can have some demo images, which are very good to play with and I don't know and try things. So, for example, if I open maybe the retina, so just to show you something, sometimes.
These are the examples in the book. We've got a book,
Yeah.
manual book
Yes.
that you can play around with and follow how to do things.
Yeah, so these are the ones, yes, exactly. So if you click in Surface and you skip the automatic creation, so I'm going to use the contour tool, so therefore I turn off the volume, so I see the signal. So let's say that, I don't know, maybe I'm working in the green channel, but let's say that I want to segment a region of interest, but of a random shape, or like in the case of the EM, you want to do an automatic segmentation of a specific area. So you can draw your random shape Roy. For example, and now in board, maybe I copy and I go to the top of the volume and I paste, and then I click create surface. So this creates a surface, and then you can use this as a mask. So this is very, I use it many times, either for any type of image. And then you can go to the edit and say mask all, and we can mask, for example, the green channel. Very important to duplicate channels so we don't destroy our raw data set. And then we can say set voxels outside the surface to 0, and we can say OK, and this creates a new channel. So the new channel only has signal inside my region of interest, which means that now I can run a surface automatically on the mask channel, and therefore building a surface for just that area. I don't know, in case it can be of interest, or I don't know, you have a time series and you only want to see the objects that are coming to this area, so you can use mask for this option.
Really, isn't it? Yeah.
Yes, like a crop, but you don't crop the data.
Yeah.
And when you crop the data, it can only be square. And this is random.
Can you do it the other way? So instead of just seeing what's inside that, you only see what's outside.
Yeah. Exactly the same. So you go into the mask options, so you say mask calls, and okay, I'm going to choose now the red for fun. And you say set voxels outside the surface to the value they are, and inside the surface to 0, or you can set your own value in case you want something to see in case you want to see it very bright or something like this. You can combine both, and you can say OK. So now we have a channel that it has 0 signal where we draw. Maybe if I go to length, we will see it better.
So then, say I had some cells that were outside, could I then just track the ones on the outside? Yeah?
Yes.
Okay.
Yes, you could, let's say, okay, stop tracking when they go inside here, and then you can build, yeah.
Where do you get the masks from again?
Yeah, so surfaces, in the pencil tab, the one for edit, and you have here the mask properties. And you click in mask code, and then you have the dialog window. So now if we navigate through Z, we will see that in here, we will see the nice hole there.
That's useful. So yeah, if you've got like a cell in next to you and you're able to look at one cell.
Yes. Yes.
So that's really useful.
That can be very useful. More questions, or shall I look at a different data set?
Yeah, can you have a look at the, here, we want to reconstruct the membranes of the cell tissue.
No problem. Give me a minute. And then stop.
So if you go to that one right at the top.
This one straight. Oh, yes.
So what we'd like to be able to do is basically be able to draw around the outside of all those cells that are shown on the it's tubulant. It's not the best for outlining cells, but it's good for keeping in focus. That's why we've chosen it. And I was just struggling to
segment these individual cells.
Yeah.
Okay, yeah.
You can see it by eye, but yeah, I couldn't get it.
So I'm just going to see. Okay, yes, this is better to look at it in mid. Okay, but this is very good because we can do cool things here, I think. We can use IMARIS cell in this one. And because we have a very nice nuclear staining here. So we can use IMARIS cell. Just for saving a little bit of time, so because the data is large, I'm just going to segment a row like this.
Yeah.
Oh, it's over time. Oh.
Yeah, it is over time.
Okay, yes, but still we can do, yeah, nice. Cool, excellent.
Ultimately,
Yes.
what we want to know is, so the cells are dividing, and we want to know if the cells are dividing along the long axis of the cell. So that's the ultimate goal. But if, at first, if we can just at least be able to automate finding the shape of the cells.
Oh yeah, you are the one dividing. Yes. The division process, can we quantify? How can we quantify the division process?
What's red? It's danced around a bit when it divides.
Yeah, that's something we're really interested in.
Okay, we'll see, because there is another one dividing here, so we can center in this area to see, because as they divide, the number of nuclei is going to increase. So maybe that will be a parameter to tell us that there's been a division.
Yeah. So the most important thing for now is to automate the outline of the cell, and then we can think further.
Yeah. Got you. So let's move this to array.
Did anyone in FitPlane use a sort of three-dimensional joystick? I know the X-ray crystallographers have strange things that allow them to manipulate things in 3D.
Yes, no. Don't know how. Maybe it will work in the same way.
I don't know.
Yes, I never used it, but I'm sure it could work. I don't know, but we have never used it. So the main idea is to have the source channel. That's for the cell body detection. That's the green channel. That's good. So now it's moving. Since we are looking at cells, normally 10% of the size of the cell. So, for example, if I measure one of these cells, so 17 microns, something like this, or 16 microns, yeah, so maybe, around, 1.5 is a good smoothing. And then detect nuclei for the red channel, and again, I'm just going to measure a nuclei to have an idea of the size. 8 microns, so smoothing 0.8, okay, it gets 0.75, so I think it's a good default value, so we go forward. So now we need to have why this doesn't expand. Oh, let me step back. I think I may have done something. Cell body, green, nucleus red. So if I see just the cell, oh, hey, I think, I don't know what's happening here. No, okay, just because it's all gray makes me think that I'm not seeing anything. But it's good because the cells, they are just basically everywhere. So that it's difficult to see, but there is a gray mask there.
Oh, okay, so that's okay.
So,
It's just completely.
Yeah, so if I remove it just to very high intensities, you will see that kind of gray mask there, but because the cell body, it just goes everywhere really. So we just want to cover all the area. Something like this is good. Okay. And now for, if I go to settings and I hide the cell and have the nucleus visible, so I just adjust this threshold for the detection of the nucleus. So yeah, and also to make sure when we have a time series that everything is nicely detected at the beginning of the movie and also at the end, in case there is some change in signal over the time series. Good, I'm happy with this. So now we go to the next step. Now this is the important thing. We need to choose the option. We can expand cell on nucleus, so if we have only the nucleus, it will try to sort of convert this nucleus also into a cell of the same size. That's what this option does. Or if there is a part of the nucleus that sort of sticks out from the cell because the labeling of the cell hasn't covered all the cell area, so this option will cover that area, while this one, it is nucleus outside cell, so if there is a part of the nucleus that sticks out of the cell, it will delete it, it will exclude it. And then the important part here is to choose, in the split option, is to choose enforce one nucleus per cell, because this is what is going to make the cell division. And now the good thing is that here the nuclei, they are also nicely separated, so we don't need to use this option. If we had the case where the nuclei were touching each other, then we will split the nuclei also. So now we move forward. So now basically it's creating all the cells and creating all the nuclear structures and everything. So it may take a little bit of time.
Is it going to look at the green channel to work out where the edge? Use
Yeah.
that bright line?
Yes, it's some kind of watershed algorithm that uses the nucleus as a starting point and then spread. So normally it's okay. It's a good one. And we also have at the beginning of the creation wizard, I choose the option cell body detection, but we also have the option of membrane detection. I don't know. It takes computationally again. It takes a longer time. And it worked okay when we were trying to look at, for example, a 16-stage embryo that it only has membrane labels, but it has to be very good membrane labels, so that there are not many gaps through the membrane, and the membrane is nicely defined at the top of the set stack and at the bottom, because if the cell is open, the software doesn't know what to do, how to close the top and the bottom gap. That's why I didn't use that algorithm here, because I don't know if it will work so well. Okay, so these are just some filtering options. In this case, maybe we don't need to apply them, but in other cases, there may be like cells, half cells in the edges, or some cells that are not properly labeled and we can exclude them and things like this. So here I'm just going to go forward, not do anything about it.
What's the little plot?
What's this?
The little plot.
This plot here.
Yeah.
This is like, for example, if we want to add filters, in this case, related to the number of voxels in the nucleus. So this is like a histogram, and it represents all the nuclei in the image. So there will be around this number. Yeah, so it's like if you had line plot, because there are so many lines, it looks like a smooth plot.
Is the number so high because it's the time course up?
Yes. Yes.
Instead of not.
Yes, there are not so many, but there are many along the whole time series. Yes.
Two things you have, but you don't have time and colour.
Colour.
Yeah.
There you go.
Yeah.
Colour's the main one.
Yeah. Quite jealous of your colour.
No, we have colour.
We can do false colour or and green from now on. Green and black. No one will know.
It's really funny because when you're sort of teaching someone on the microscope, they look, when you see a black and white picture come up on the screen, you can see the disappointment in the faces. And then you sit over it and they just start smiling like they're suddenly happy. Green. Oh yeah, that's right. I can see it now.
Yes, so a little bit of time consuming, since there are many cells being created, split over all the time frames. Do you have any questions I can answer in the meantime?
Could you kind of crop it in time just while you developed this bit? And then
Yeah, I
apply
mean,
it the whole time.
Of course, not now that the processing is already going, but maybe I could have cropped it, let's say, to just have the time series, yes, and just work. In fact, maybe I could have cropped the data set from the beginning to a small region of interest and maybe crop in time, and then this would have gone much faster.
Can you do like an ROI that's cropped in time?
No.
So
No, you have to crop
the actual thing.
But then can you apply the thing created to the whole data?
Yes, because So now we don't want to detect physical. Okay. So this is in case you have physical-like structures inside, but we don't have, so I don't select it. So yes, so because what happens when you create, I don't know, surfaces, spots, cells, or whatever, you have that little creation wizard, and in there your settings are saved. So you can remember your settings, and then you can have your whole data set, load your data set, load your settings, and run.
When you say remember the settings and load them, would you actually just have to quickly write them down? Or is there a way
No,
to
it will be saved here, and then you can say remember parameters.
Okay.
You call it
Right.
whatever
Okay.
protocol you call it.
Yeah.
So I don't know, test or something. So that means that if I create new spots, I can load parameters.
Where do you go to save it?
I'll show you now, when maybe here in the screen. So here now we get to establish the tracking setting. So how much so it's all an autoregressive motion algorithm as default. So we get to set how much the nucleus moves. So it's a very small movement. If I make the grid a bit smaller, maybe you don't see it here, but there are little grids there. So let's say now the grid is 10 microns. So now if I move from one frame to the next one, I don't know, probably the nucleus doesn't move more than 5 microns, so has a...
It does when it divides, but does that not?
Yeah, but when it divides, it will be a new one, right?
Yeah, okay.
I will imagine. So
Yeah.
I'm looking at this one, for example, see if there is any other one. Don't tell me I didn't catch any dividing one. No way.
Yeah.
Okay. Yeah.
There was one at the top right.
And this one is fusing a little bit. Yes, sorry?
Up at the
this
top
one.
right, that one there, just where you cursor down, but if you went back, I'm sure that
What were you looking for?
a dividing cell.
There's definitely done in there. The one in the middle of the line.
Oh.
At the beginning there was one that's right. Yeah. In the process. Yeah, that one.
That one, yeah.
That's there.
Oh.
You keep going. Oh yeah, there's one there.
Yeah.
There's also one just below it to the right.
Yeah, but that's good because then, for example, when it divides, this one still is within that maybe 5 microns. And then just that one that separates, so I think it's good. And the cell, yeah, probably the center of mass doesn't move much either. So, so I just set it up to 5 also. Okay. And this I'm going to set it up just to 1, this maximum gap size, which means if in case I miss a nucleus escape detection from 1 or 2 time frames. So this, for example, the device by the signal is quite weak. The 1, 2, 3, so maybe 3 frames. So see if I can pick up this one.
That's frames, is it?
Yes, it's frames, yeah. And this is another one that divides, okay. Yeah, but still when it divides, still, yeah, I think they still move within 5 microns because this, you can see the grid. The grid is 10 microns, but in the screen I can see maybe they don't move more than 10. Okay, just give it a go and see how it works.
Did it get dimmer because the epitopes didn't?
They go a bit, I think they go a little bit deeper when they're going through anaphase. They get a bit weaker in anaphase and then they brighten up again once they're nuclei.
Cool. Nice, so this is now all the tracks. So in case you want again to filter any trajectory, but I'm not going to do anything. Finish. Okay.
As all the tracks are moving in the same direction, that's likely to be the stage is drifting.
Yes, and maybe some of that will be a little bit of drifting. Hello. Okay. So that was the last step. So hopefully good things come for those who wait. So let's hope it has done a good job. So now I just put the volume rendering and the cell. So now you can see how the software has split
How do they match up with the actual?
the cell. So yes. So we are missing some there. Could be just for a specific frame because maybe the signal was low, or I don't know, maybe if I put some of the filters to
Can you change the colour of the reconstructed cell? So
yeah, we can
see the fluorescence through.
Yep, we can make them maybe
See how well it
gray and make it transparent. Okay, a little bit. Okay, let's try to do something else. Let's try to put a clipping plane. 100% speed. And let's move it below the volume.
This is a clever trick, I didn't know about this.
And maybe now we need to make them solid again because we can't see much. And I don't know, I'm trying to see what is the best way to look at it. Okay, maybe now the keeping thing has to be on top of the volume.
Not bad, is it? A bit off in places, isn't it?
Yes, because depends on the signal, but
Maybe a bit fiddly around. So what could we adjust to try and improve it? If you look at that one right on the left hand side in the middle, it's quite a long way off.
yes, the thing with this is that once it's
Kind of like that one.
this one here, once it's like this, you cannot really edit it.
Yeah. But could I go back to the beginning again? Is there anything I could do that?
Not really, I don't think.
Deconvolve the data remember. You know, so it becomes maybe
Yes.
sharper membrane.
Maybe the convolution could help. Yeah, maybe the convolution could help. I don't know.
We do have a membrane GFP as well, so we can try the same with that. Trouble with that is it's only in a very you see it well in a small bit of the cell, it goes out focus very quickly, whereas tubular because
or just get a high, use maybe a higher numerical aperture to get a smaller region of interest, but with higher detail. So then you can get a better, because the good thing of to have green fluorescence everywhere, because if I go through that, because I don't know, we have a membrane staining, but I don't know how well it will work in this data, because the membrane label.
Your brain says that's really clear if you try to get the computer to see it.
Yeah, because
that was better than I managed to get the computer to do it. So
yes, because what happens here, or maybe you just need just a few more steps or something. I don't know. I don't know. Because if I look at the membrane label, membrane algorithm to work, the cell needs to be closed, basically.
That's using the other detection method.
So, for example, if I open, can I open a new one? Okay, I'll show you. Okay, maybe I'll show you later. I'll show you an example of a demo. Like, for example, if you look at an embryo, a 16-stage embryo whose membrane label, it really goes, it collects all the cells from the top to the bottom, so you have that continuity in the membrane, while these, they look like flat, they don't have bottom, they don't have top, so therefore the software doesn't know how to close that membrane, and that's the problem.
And that's why you did the cell body.
That's why I did the cell body detection, which in this case, to have that signal there, it's kind of good in a way.
So with what we have now, as far as the trace of the cell, what can we
So what we have here now,
can you take like those outlines and put them into other programs if we want to quantify them?
so what we have, maybe we'll make the cells transparent. So I think maybe the settings could be optimized just a little bit more, maybe. So now it's calculating the statistics. So then, of course, you can follow the movement of the cell, like, okay, in terms of distance that it travels, or if we look at total number of cells and nuclei, we could see if the cell is dividing.
Could we look at cell shape?
And you can look at cell shape, yes. So for example, for the nucleus, maybe the shape of the nucleus is important, because when it divides, it completely changes the shape, suddenly collapses, it becomes very small, and then it starts, I don't know, if it's not so rounded or something.
So the other thing, I suppose, with the way that this works is the shape it's making, it's kind of doing fried eggs, isn't it?
Yeah.
Which is not actually, that's great for cells in a poultry dish that often look that kind of shape, but it's kind of putting that shape onto these where they don't look like it. They don't, the edges don't go in and out like that. Does that do with the algorithm?
Yeah, I think that's to do with the algorithm, how it tries to split the cells depending on.
Pushed up against each other, rounded.
The kind of way they go, whereas actually, because they're in
more like pomegranate.
Yeah, it's not. Yeah.
I mean, they're actually quite straight edges, whereas
Yeah.
giving them wobbly edges.
Yeah, because this is to do, at the end of the day, this is just a watershed algorithm. So it tries to look for valleys of intensity. So, because also the signal is not uniform, I think that's where the problem is in trying to find the right age.
It's quite speculative,
but
actually, high low intensity.
Yeah.
So if you did a
Yeah.
first.
Unless you could try to get like a higher numerical aperture and maybe to get a bit more set of stacks that collect properly the top and the bottom.
We're kind of limited in
But
it has to be a dipping lens. We could do
all right, yeah.
but it's not.
Yeah. No, you got it, yeah.
But it's
already
getting
do.
there. But I just wondered, why
Yeah.
it likes to give it a wobbly edge, why it can't connect straight between 2 points.
Yeah, it's because of the algorithm used to split the cell.
Because it is making them look like
like
tissue culture cells.
Yeah.
Right? That's what the overlay looks like to me. Whereas in actual fact they don't. If they're in an epithelium, they've got straight edges. Is that something that could be corrected if we?
I don't think you will have a quick fix. I don't think it will be fixed in the near future or anything like that, unless the cell membrane algorithm is improved somehow, that it can cope maybe better with this kind of situation. That's the only thing I can see. Yeah. Yeah, so then we can look at the number of cells over time, the number of nucleus over time. So it decreases, interesting. So it gets a peak there, and then decreases a number of cells. Oh, that's interesting. Yeah, I need to look. I will have to look with a little bit more in detail to the data to understand a bit more what is doing. Because these can only be due. So these are areas where there is a cell, but there is no nucleus. But I don't know from where, unless it comes from the edge or something. Some cells in the edge that they have no nucleus. That's the only thing I can think about, this difference here. Yeah, that could be.
the number of nuclei shouldn't really go down over time either.
Yes.
Because it is reconstructing the nuclei, right?
Yes, it is. Because I saw that there were some points where the nuclear signal was coming together, but they were two completely different nucleus. So if I put cell of like, and this is what is making the number of nucleus decrease, so maybe we should have used the option split nuclei also. There was something. I need to see the signal up. So the earlier, and now I can't see them. Like these two here now. I don't know if it's, oh no, not quite yet. I think these two, they get very close, so suddenly become one. Good. And that is probably what's making the nuclei suddenly to count just as one, as opposed to two separate ones. So yeah, maybe I should have used the split nuclei option also to make sure that they are separated, because that's what's making that little dip here in the data. Yeah.
And it maybe isn't seeing two new ones, two separate ones. I can't see with the tracking, the moving apart. Anyway,
Yeah.
move on to the next.
Yes. But anyway, these are a little bit the possibilities. Maybe this. So regarding the settings, so when you click here, these are the settings. So you can click in Remember Parameters, give the parameters a name. That means that when you open a new cell, you can say default, or here you will load your parameters, you will find them there, and then you can reduce them. And here is where you also find the cell membrane algorithm here. Cell body and cell membrane. Do you want me to save this data set?
Yeah.
Yes, just in case.
It's useful to go back to.
Save as. Here. Oh, it's already in the right folder? When? Oh, yes. And.
Yeah, I've copied everything else. So just save.
Okay, yes, save. Okay. Yeah, so maybe if you want to give it another go, just cross-sense the data to something small, so you don't wait too much until you optimize the setting. And then when you have a better idea of the settings, how those can be optimized, then you can work with a larger data set.
So that it'd be really useful to report back to the programmers that making the edge wobbly, because I'm sure there must be quite a few people wanting to get epithelial cells.
Yes.
And, I mean, I'll try it with our better probes. It might not be as obvious
We've got a way of doing it where you basically grow from the centre, and so when it pushes up, it flattens out all the edges. That's on a high content. But that's like more of a static ROI. That's kind of grow them in the first place, and then that just gets kind of propagated through time. It's not dynamic. So that's the way it gets around this. From a nucleus, you can then keep growing out, and it knows that, well, in between, take this, but then it takes it on fluorescence as well. And you end up with, these pushed together on the ground. See the pattern there.
It's just one of those smooth edges, really.
So, just to briefly show you.
It's the smooth middle and make it less inductive and maybe sort of like more of a boundary, isn't it? Make it centering more. If it does all drift.
And we'll probably don't even need to do it over time.
I think you can just open the application as a folder.
Okay, so if I click, it will open it as a folder?
I can't remember. Right.
Yeah, content. Okay, yeah.
Looking at it.
Yeah, well, 50-50.
So,
I have to run off. But thank
no
you very
problem,
much.
you're welcome. So just quickly to show you that sort of cell membrane. You see how for example, if I go into a slide, so you have a cell membrane quite similar to yours, but the difference is that this one also goes to the top. So it closes the cell.
And you did membrane detection on that.
Yeah.
And how does that look?
And then once you do that, this is a bit how it looks. So maybe I'll remove the volume. Or maybe we can put the volume, but in it. So
we'll try with our membrane GSP and see if
and see, yes.
it's less wobbly.
Yes, just just so you don't feel just apply just a small image, short time lapse, or even just a static, just to see how no much point to spend too much time with them. The algorithm is not going to give you good results, so just to give it a go. But that was the idea of the cell membrane. So, shall we look at different data sets? Any?
Yeah, so I have those
Okay,
axons.
so let me see a little bit. Oh, okay, yeah.
Filament tracker.
So, Tomas, yes?
Yes.
Okay, so what's the name?
Adam.
Adam, okay. Ooh. I don't know. What do you plan to?
There's one at the front.
Okay. Oh, so maybe you can eject yours?
Yeah. So pull mine up.
Yep. Okay.
I think we're going to come back to the measurement first.
No problem. Yeah.
Great.
Excellent. Absolutely. Okay. And should it come up here or something?
Yeah, data bar is, I think, that one.
Okay. And
so if you go to work, and then IMARIS workshop.
Yeah.
Now I have a few examples, so probably the best is the cytoskeleton 60X. I'm not sure how good quality we need to
Okay.
And then, so I have this ND2 file, which is from Nikon.
Yeah, very good, yeah.
So we can try open this.
Yes,
This is the
that's the
original,
best.
but I wasn't sure if you can open actually this new format. So I also copied some zip
Yes,
files.
we can. We had a lot of trouble.
Because I still have problems with image, I cannot open it properly.
This was a problem everybody had.
Yeah.
Because Nikon, what happened is that suddenly they changed the format.
Yeah, they upgraded the
and they
software.
upgraded and they say, and they didn't tell anybody or they didn't communicate, and and or maybe they wanted just to use nice element software or something, and they didn't share the reader with anybody.
Yeah.
No image, nobody, and then people was like, oh, I can't open this, but
Yeah,
yes,
especially
yes.
this is a multi-point
Yeah.
file, so I have like 3 points. So
Mhm.
it's 2D image. There's no Z stack. It's
No.
2D image in time.
Over time, yeah.
Over time, and what I'm interested in is the branching of axons.
Mm.
And I have actin and tubulin stained with
Okay.
red and green. And yeah, so it will be the first time I will.
Okay, let's see how the signal looks
filament,
like.
Yeah, filament.
Uh-huh.
tracking.
Yeah, because
So-
tracking of filament. Wait, if it's only 3 points, it can be done. If the automatic doesn't work, it can be done manually. Or is it too complicated, the structure?
Well, you will see.
Oh,
It's not
we'll
very
see.
complicated, but it's quite dynamic. And then
Okay,
we have
okay.
this protein which we think that regulates branching. So if you manipulate the branching point, what we would like to see is the different number of branching points, or the time span of the branch, or something like this. So then if you have different conditions, probably.
Okay, let's see. This sampling open. So, okay, nice. Oh yeah, it's only one, but okay. So since the data is very big, I will, if you allow me to crop it,
Yeah, sure.
because
So-
otherwise we will be
But what we are
forever.
looking at, we're looking one point right now.
No, this is just a preview of the data. So
Okay.
now
So
can
if
navigate.
you copy, basically, I think this one is the most interesting. It's more active in terms of actin
Okay.
filopodia
So
formation.
yeah, so maybe we can crop. Something like this.
Yeah.
Okay, and time points we have something like 400. So.
Yeah, it's every. I think this one is taken every 10 seconds. So.
Okay, can I open maybe just 100 frames?
Yeah, try.
Just to make the size smaller.
Yeah.
And see.
So actually, there are 3 channels. So red, green, and bright field. I suppose you can remove bright field.
So we could have removed also. Okay.
So green is tubulin, and red is actin.
Okay.
So now you
So
cannot see very well actin actually.
I'm just saturate it a little bit so you
Okay.
can see it also in the screen. Oh, I see. And you are interested in this fit?
Yeah, so I'm interested in formation of those branches. So something like this. And also there is a difference. So when the branch is forming, then the first step is formation of actin filopodia. And then during maturation, tubulin is going into this branch. So if it's possible to distinguish between those processes.
Okay. This is difficult.
So why it's difficult? No, I mean the question is, so
Yes.
is it because of the data, or is
I
just
think it's because a little bit, for example, this signal is very weak.
Okay.
So if I compare, for example, some of these speckles with these speckles in the background,
Okay.
I know. I mean, the image is wonderful. Don't get me.
No.
There's something in terms of how the software works.
Yeah. So for me, it's also important if I need to, for instance, improve something, acquisition of this data.
Metric convolution. I don't know if it could help a little bit. We can try. We can give it a go and see what
Is that
happens.
actually connected? You know, the one that's gone dotty. Is that
Connected
actually
to
a
this
filament?
one.
I have no idea.
Okay.
It's difficult to say. It's 2D, so so the idea of the experiment is to manipulate this protein which we are interested in, and then have like two sets of data and compare, for instance, the number of branching points or number of branches only with actin, which don't have. Or also because in time you see, so they are very often they are retracting.
Yes.
So then it means that the time span is different probably for different ones. So I was wondering if you can calculate the time span, how long it exists.
They grow and then retract. It's very beautiful data set. Okay, let's see what it can do, because I never got to analyze something like this, so I don't know. I cannot tell how well it's going to work.
Okay.
So let's try. Because what happens?
You can also look at tubulin curve. That's all.
Yes.
So, but I suppose you can threshold it somehow, so you can get rid of this weak branch and then just keep those stronger.
Yeah, definitely.
So
okay, I thought this one could be also of interest for you. But okay, let's see what we can do. So let's work first with the green channel. Perhaps here a little bit of the artificial thing that we need to do is that this needs to be treated a little bit like a neuron. So it needs to have a soma, a starting point.
To have for the software.
So because it will treat everything like tree-like, and from the soma we will have all the branches, all the dendrites or filaments spreading out. So, so this is what the starting point is. So maybe, and I don't know how this will work in the first instance, because the starting point is 1.5 microns. Let's say 2, because this is a starting point. I want it ideally to be somewhere here, but the software may put it anywhere it wants, because what happens if we look at a neuron, the neuron has, let's say a big trunk from where everything branches out. So then it's easy to differentiate the size of the trunk. That's why this can have a very large size versus the size of the filament or the dendrites. In this case, we don't have such a thick trunk. So if this is a trunk, the starting point can be placed here, here, here. This could change. So I don't know how that is going to work. But if what you are interested are in these branches, maybe the result maybe it doesn't matter.
Yeah, for me probably I suppose you could take like this and look at those branches, for instance.
Let's see what happens.
In this case, just for to see
and
what
then,
the software can do actually.
Yes.
Axons and
yes, and see thinnest diameter. So this will be my thinnest diameter. 0.
So you need to define manually
this setting. So you have to set up some settings. So I need to tell the size of the starting point. So I set it up as the thickest diameter for the filament.
Everything which will be smaller than 2 microns will be treated as branches.
No. This you have to think in terms of a neuron. So
these are neurons. So.
Yes, but sorry, but of a full, because I'm trying to think of how the software may try to think. So for tracking the software, for the algorithm to work, basically you first need to detect the starting point. So the starting point, you have the big soma there. And then you have your dendrites. Or your axons. So this is your big, the structure of the big diameter. Because in here, we don't have such soma. We can only define it as to be the diameter of the filament. So that's what I mean, like the problem now is that over the time series, the software can place the soma now here, then there, then there, depending on how the signal changes. I don't know.
Okay, so
that's what I mean.
Software you
because it needs this starting point in order to calculate the branches. And then the following diameter, this one here, refers to the thinnest diameter of the dendrite. So in this case, this thin diameter, or if we wanted to detect this one, this very thin diameter, or that very thin diameter. That's what it is. And when it's you have a full neuron with the soma and all the dendrites, then it's very easy to detect where the soma is and where the rest of the structures. So you will see now.
Because actually the other data set is from, because this is from explant, so I cut spinal cord into pieces and then I plate them, and then they are growing from those pieces. So there is in other file there is this big piece which you can see, which you can treat as a soma, I suppose, and axons growing out of the. But then it's with 40x, so the quality is not so nice.
Let's see what we can do with this. Let's see what we can do with this, because we need to be able to, I don't know, to test. So this will be more around 0.6 microns. Okay, so let's say 0.6 better. So now all these blue dots,
they are starting points.
They are starting points. So we have this threshold that limits the number of starting points. So
it's not possible at this point to add one manually, like in the edit tool, you don't have that feature.
You can add one manually. The problem is because this is a time series, and now we have only 100 points, but if you have like the 400 points, you do not want to add it manually all the time.
That means every frame you need to add it.
Yeah. So now you see the starting points are always coming from the highest fluorescence. So what I don't know is what.
Okay, so there is no way to define a trunk, let's say, and then just count the branches from the big trunk manually, and to define the trunk manually.
Yes, but you will have to do it for all the frames.
For all frames.
So I'm trying to do it as automatically as possible, because you had your data set had nearly 500 time frames.
A way of doing it in image J would be to just do an ROI and do it so it's stamped a big blob in every frame before you open it.
Before this, right.
Because then it'd be kind of a false blob starting point.
Yeah, because actually very often I don't see the soma because these are explants. The problem is that the axons which are very close to the explant, they are not in focus because they are a little bit above the cover slip. And then they go down, they attach to the cover slip and they grow. And that's why very often my data looks like this.
No, I understand. I mean, and it's a very nice data. It looks quite nice, but I don't know how to solve the problem of...
If you open it in image J, we could put blob on. If you've got a data file that's not the ND2, image J.
Yeah, there is TIFF file, so we can open the TIFF file.
I don't know. Let's because I don't know which I don't know is how this will work if we don't have a soma. It will have, I don't know, maybe something like this, but of course it will change. Because if we do not have a soma, you will have something like okay, let me save this for a second. I just want to do a quick test first to know if the algorithm runs for a neuron who does not have a soma. So this is what I mean. So if we don't have soma, like here, like this, we don't have soma. I think. Like this, we have no soma. Let's see if it works. Continue anyway. Yes. I don't want to detect spines. I want to see the result. But no, it doesn't work. It doesn't work. Okay.
I have a lobby image, Jay.
Try. Do you want to try? So just you can try to. I need to. Sorry. I will just go to the toilet. I will be back in a second. So maybe you can put that block or something.
So
I think you need to open TIFF files.
which one?
So channel 1 and 2, yeah.
Oh, each one's a separate channel.
So yeah. Do we actually have this module, this filament tracker here?
No. Some groups will, but we don't have it down in the imaging facility.
Okay.
Not filament tracker. We've got the IMARIS
but
localization.
There are groups at the university.
Well, Sarah does.
Sarah does.
This is
perfect. Okay.
How many other groups?
I think it's about 4 groups. There's the Papalopoulou and Amaya. Okay, and then us, Sarah, and I think one other group does somewhere.
And everyone has to buy each module separately?
Yep.
Okay, so I'm from Amaya group actually, so
okay.
I do have it.
Yeah, so the red is channel.
So it's red, green, red, bright field. So it's red.
If we look at this, this is the
red is second. C2.
Green is
1. Yeah.
And
this
grey is 3.
Okay, you have two first two, so right you need to change for two. Channel two, right.
1, 3. Okay. Right, so where was it? We wanted it up here. Is that right?
Yeah,
It's
so
upside down,
we
yeah.
cropped. Yeah, this is
So if we make a
but there's not much happening here. So I think if you do it here actually on this axon somewhere here for instance.
down here.
Yeah, we want it to be connected. I think with this one.
Oh, I see. It's composite. I don't want composite.
So I think this is the most clear picture here. So.
Let's stop that. Didn't want the composite, so it was.
I think we can forget about the bright field, so we can put down.
Okay.
Yeah, we just need those.
So channel
red is 2,
2,
and
green is 1.
yeah. Okay, and if you put it somewhere here, I think it's the best because then it's connected and it's kind of.
I wanted to delete it from all the outlines. Was that doing it through the whole stack?
Oh, you were just copying and pasting the block
Yeah.
to all. Okay, that can be done also in IMARIS.
Ah, that'd be easy.
Okay.
Yes, that can be.
Yeah,
Okay,
just make
yeah, good idea. Good thinking. Yeah, know what you mean. I thought it was something else.
No,
that
just
you were
to make
trying.
a blob.
Okay. Yeah.
Fake.
Yes. We can do that. Also in IMARIS.
Okay.
So I did save the image. Oh, I think it was this one here. Yes, good thinking. Okay, yeah. So then we can fake a soma.
Yeah.
Yeah. I like that. Let's get back the signal, and that can be quite easily done. So maybe we can fake a soma here, and maybe for this other filament maybe here, something like that.
Yeah.
And let's see, because those points are okay. So what we do, we first do surfaces, and then we just skip automatic creation.
Okay.
Because I'm just going to use some of these drawing tools.
Okay.
Here in mode, I can select the circle. And normally when you want to start drawing, you need to be in select mode.
Okay.
So the shortcut is always the escape. Yeah. And then I want to click in draw. So now with the wheel of the mouse, I can create a soma just by clicking. I create a circle there, and I create another circle here.
Okay.
So I don't know, 2 starting points. And since there are no more frames, I don't need to draw that anymore. And I say create surface. So now I have these 2 balls. Now what is happening is these 2 balls, they are only in the frame where I draw them. Nothing to worry about. So I go to the edit and I say duplicate to all time points. Because we want to make this, as automatic as possible. So now I have that for all the frames. So now what I need to do, I need to create, but this has certain thickness.
Yeah, actually, I think there are 3 Z plates.
Okay, so let me do it again because this now is too flat.
Yeah,
This is not nice. So let me delete.
Now when we're opening stick files, I saw that.
Okay. So sources, let me delete this, okay? Yes, so let's start again. Sources, skip automatic creation. But here I only see, oh no, yes, there are 3. Okay, very good.
Okay.
So now again, circle, I just want to see the signal and 100% fit. And now I create a soma here. Now I create a soma here. And now it's in plane 1. So now I go to plane 3. Actually, no. From plane 1, I go to board, copy. Now I go to the top and I say paste. So I make sure they are in the same position.
Yeah.
And I create the surface. Okay, sometimes it gives the error. So manual stop resolution. Now we have the surface. Sometimes it gives you the error message like, oh, I don't have enough resolution to create the surface. So when you have the error message, that switch between resolution between auto and manual and put it to the highest. That's all. So now, yes, we have the 2 surfaces there, and we go to edit, and we duplicate them for all the time points. Okay, so now I have a time series with that surface repeated over time. Yeah?
Yeah.
So now what I need to do, so for example, if I want to work with a green channel, is because what happens, yes, we have the surface, but we have no signal, so that is of no help for for filament tracer. So I need to create a channel that actually has some artificial green signal there. So let me just check. So you use, okay, so I'm just checking your intensity ranges. And now what I'm going to do is going to the edit tab. I'm going to use, see the mask properties. It's so useful, this tool. So mask all, and I mask the green channel. Very important, duplicate channel before applying mask. So I don't do anything to the raw data. And then I say, set voxels inside the surface to 4000. Yes, a high intensity value. And apply to all time points. Okay, so, okay. So now, hopefully, this is applying now the mask, and we will create a new green channel that we have the signals from
Okay,
your
so
green
the
channel.
mask is the real channel, the real signal plus the surface.
Yeah, so now we have that kind of funny green channel that it has the artificial soma. So fingers crossed now. We can see that. I love it. Yes. So that's good, I like it. So now, okay, we can come back. Maybe I just throw away that filament that we did earlier. And we create a new filament. No surfaces, delete. We create a new filament. And yeah, so we go next. And we choose the mask channel.
Okay.
And okay, what is the diameter of the soma? Easy peasy. I measure it. 14 microns. Okay, so I'll come back to source path. And this is a good thing because actually now we'll make sure the soma is always there. So I think it's good. Now, thinnest diameter for the dendrites. So again, in a slide, we said, so now we need to find some of these little protrusions. how do you want to quantify this perfusion? As dendrites or as spines? Because it could be quantified also as growing and retracting spines, while this could be your main dendrite filament.
Yeah.
How does it make more sense? Maybe as growing spines or something.
Yeah.
Yeah, okay, let's try. So the dendrite then, it will have, yeah, because it's quite a big difference in diameter, so I think it makes sense. So we can measure this diameter around 1.3 microns. So, yeah, 1.25, I think is a good. So we go next. So now, of course, we got a good soma detection. Perfect. Now I'm just going to make the channel transparent so we can see. Now the idea is to have some of these little balls along the dendrite.
Okay.
So these are the
what
thresholds.
are those small balls?
Yes, I explain now. So the first threshold is for the soma. So as I move the threshold to lower values, more soma starts appearing.
Yeah.
So I just want the two.
Yeah.
And hopefully will remain constant over the time series. That's the good thing of having such a big soma. Perfect. Now the little ones, they define the path of the dendrite.
Okay.
So if I'm interested also in this dendrite, I need to move this threshold to lower intensity values. So
Okay.
more
Uh-huh.
spheres start appearing in dendrites with lower intensity. It may happen that here it tries to split the dendrite, like half belonging to this and half belonging to the other one. I don't know exactly what, or just arriving to here. I don't know exactly what it's going to do. But just to warn you that it may be, let's leave it something like this. And let's see how it goes over
But then you
time.
have also those two spheres here, which is actually the growing branch.
Yes, but then I think those we will count them as spines, so as branches.
Okay.
I think we can count them as branches.
Okay, let's see.
Let's see. Let's try. Okay, so we go to the next step. Okay. And then also, for example, this remove seed around starting point, that makes reference up to what point you want to start adding seed points. Yeah, so maybe that would have been reduced, something if we wanted more seeds around here or something. Now this is just a step to specify the diameter of the filament. So okay, we have to get a pic. If there is some stuff here, don't worry, because it didn't have a seed, so that's no problem. And here you have two different algorithms how you can calculate the diameter. So one is the shortest distance from distance map. That means that You take the center of mass of the filament at a specific point, and it calculates the diameter as the shortest diameter to the border. While this one tries to take the average diameter around the cross section. So normally, because in XY we have more resolution, you are better off with this kind of diameter calculation in order to not to include some of the set distortion.
Right.
Because in set it looks bigger the diameter, but it's not, it's just PSF.
Yeah.
So we can choose that one. So you can see now already here where it's trying to link that little piece there, because the two filaments were kind of getting together. Here the signal was decreasing, but we have to compromise. And now again we detect the spines. In our case, the spines are going to be these little protrusions here. So again, we need to know the diameter. So for example here, let's see if I'm in the right set. Yeah, here 0.5 or 0.6 microns. So thinnest diameter 0.6, and then maximum length. So the maximum length that they can reach from the main trunk to the end. This is just in order to separate what is a spine to what is a dendrite. So I'm going to have a look how they grow. Just saturating this a little bit so I can see up to where they can stretch in order to get a measurement. So for example here it can be maybe around 18 microns. Okay, let's try that distance. Let's see, it was not too bad, the defaulted value. And now we will have again those seeds that hopefully we cannot see them now. Okay, so the blue seeds are now the spines. So obviously now, actually, do you prefer to detect the branches in the red channel?
Yeah, actually I would like to do it more at the end. So
okay.
You can do it in red for sure now, it's fine.
Yes, because to do it in both, then that means that you have to do the segmentation first using the green and then using the red. Unless you create a new channel which is the sum of both.
No.
But then that makes no sense.
No.
So let me, and the reason why I like the red is because the signal of the red is much stronger.
Yeah, because it starts from actin, protruding from the trunk, and then
because then you can quantify the green signal inside.
Yeah. Okay.
Okay. So so let's
that's perfect. That's actually what I.
Good. So let's step back, and here rather than to choose the green, we choose the red.
Okay.
So yeah, I like this also better. So now hopefully we have all these little seeds that specify the path for the filament. If at some point you think like, oh, I would like a seed here, So you just go into the into the select mode, and you make this cube the size of the spine, and you do shift left click to create Finder. Yeah. So the important thing doesn't need to be all full of spheres, but just a few, so they, because then basically it just joins the dots. Yeah. So we have to make sure we have some dots there. The same way if we want, for example, this little one here, and make sure that is something that is repeated over time, because any modification we do is only for a specific frame. Okay. Okay. Yeah, so this is something that if you want to spend a little bit of time in terms of doing a nice editing, so maybe this one, I can delete this.
But then you need to do it for every single frame.
If you want to do editing, yes. If not, you can just work with the default settings, the automatic, because I can understand a 500 time frames data set, so yes.
How do you do a sum of the red and green channels? You know, you were saying that, hey, could you do that?
With MATLAB, with
okay.
here image processing, you have a channel arithmetics, and you can do whatever you want with the multiply them, divide them, sum, rest. Yeah, you can do whatever you want with them. Okay, so okay, so let's say that we are happy with this. Actually, I'll make a note to remind me to tell. To tell Sarah how to connect TXT about activating. Oh, Sarah, I may, if it's possible, could I get a little crop of your data so I can send that to the developers? Because then that's the best way how we can improve either the cell membrane detection or.
Yeah.
So I will ask you for that. So this again is the same as for the dendrites, the same type of algorithm, same as we did before. Oh, I'm quite curious to see. And the same for you, I may get a little crop of the data, because sometimes it's not so frequent you come across to these data sets, and they are very interesting indeed. So now this is the time analysis, the analysis over time.
Okay.
So we need to establish okay, track filament center of gravity. So I think this refers to the soma, so it doesn't really, the center of gravity doesn't really move, so we can choose something very small, 1 micron. Now track dendrites, this is how much, for example, we want to track the terminal points. So these points here, how they...
Okay, so then the length.
Yes, how they, rather than to track the branching point, how the branching point can move up and down over the filament, we want, I think, it's better to track the end point so we know how they expand or retract, how it grows. No? Or, no, you tell me.
I don't know, so...
Because these are two
I think
different
probably
options.
more interesting will be to know the number of branches.
Okay, yeah, but that's different.
That's different.
That's different,
Okay,
yeah.
then-
So we can track the terminal points. And I need to know how much they grow. So for example, just if I look at those terminal points as a reference, again, my grid is 5 microns. Okay, let's see, maybe around 8 microns. Okay, I don't know. And now track spines. Again, we can track what is best to track. The terminal points, and yes, maybe these. Maybe same kind of distance. I'm just guessing a little bit because as I said earlier, it's not that I'm so familiar coming across these data sets. So, okay, so now we can see also the branching points. Okay, let's see, we go into the statistics. Okay, let's see, detail, filament. Filament number, spine branching point. Okay. Okay, let's see. What? So you want to know how many branching points?
Yes.
Well, this is equivalent to how many spines?
Yeah, fine.
Yeah?
I think, you can
So,
say that.
because this will be the red
Yeah.
point, so we can look at filament number of spines. Filament number of terminal points, this is also equivalent. So this number here, oh, Okay. Okay. So hopefully this number here is telling us how many endpoints we have per time frame. So now we should have 19 for this filament here. So let's see, let's count and see if it makes sense. So for that, I want to see this as a line. And hide the signal for a second, or maybe as a cone. No, sit in there. So that will be 1. Sorry, now a little bit too manual. 1, 2, 3, 4, 5, 6. Is this counting it as multiple? I think so. Why? If we look in line, these are multiple.
Yeah, it counts as
Are they really multiple? Okay. Yeah, don't know why it's counted as multiple, that one. Or maybe we can count attachment points. Attachment points. So if statistics, maybe here attachment points. Filament number. Number of points per time point. Don't know what is this. Oh, interesting. I was trying to look, because normally filament, what it tells you is a total. For example, a filament in this case is defined by all this green structure here. This is a filament, one soma, one filament. Okay. And it gives you all the characteristics of this filament. So I was trying to look at if we had something like total number of attachment points or spine attachment points per filament. But I didn't sort of saw it. And this one, the problem here is that the software somehow here has calculated like 3 spines, which is just really 1, which I don't know how we could correct for that. maybe making this, maybe optimizing on maybe the tracking parameter, the size of the spine to make it a little bit larger. I don't know. Because branches, this is different. This is not. So I think branches refers to dendrite. I will need to play a little bit more with the data set to see what statistical values. So what would you like to quantify?
Everything which is possible.
Well, yes, but for me I can say, no, for me this is interesting,
me,
and then it could
for me,
be
branching points. So basically it would be those points.
Yeah,
here,
attachment. Yeah.
or attachment points.
Yeah.
And then and then the difference between red and green channels. So how many of those branches have both colors, so actin and tubulin, basically.
Okay. Yeah, the difference between the green and the red signal.
Yeah, and then I don't know if you can measure it. For instance, how long this branch exists. So let's say those 3 parameters.
Length of branch. Okay. So, all right. So if, for example, I select that branch there, even if the software thinks that it's 2, then you can follow the length over time. Why hasn't established the tracking? This hasn't been showing. I need to play a little bit more with data sets to see what is happening. I need to, because I think I need to optimize a little bit more the settings and and see what is happening. I don't know.
Well, once you've made those little side branches, can you get back to kind of a volume, so you could look at the intensity of the green and the red inside those little side spines?
Yeah, so the thing is that once you build, you have a filament. You can have, for example, you have a spine. So if, for example, I select this spine, is that selected? Maybe not. Okay, let me see. I don't have intensity values. I have intensity center. This is not good. Spine terminal point intensity center. But I want the whole spine or the whole branch or the whole dendrite intensity. Interesting, because we don't have here. I was trying to look for something like dendrite intensity or something like this, but there is none of that. So that means I cannot report in intensity, which is a bit bad. Because yes, you can segment them with surfaces, but with surfaces, what will happen? I think it will be complicated because of the low signal, and then you will end up segmenting. You will end up segmenting the main filament, but not the branches, unless you do a mask where you subtract the signal from the filament. If you know what I mean. So you will have to remove all this bright signal in order to be left just with this signal. Then you can just build surfaces and track them over time and follow the signal inside. Let me get back to you with this data set. It's a beautiful data set, so I'm sorry we cannot do a little bit more about it, but I will get back to you with something. Even if it's bad news, I will get back to you with news.
No, it's alright. As long as I find it.
Yes, but it's an interesting data set. So yes. Yeah, I will get back to you. So let me, in any case, take this. I'm losing track of time. So now we can look at Tova. We can look at your data set. You said they were here already?
One is, yeah.
One is.
Not, you want
But if we
track,
generate
don't
some
you?
tracks as we go along, then we can get the stats anyway. So just load the one that's on there.
So I can take my.
Yes, let me use it just for a second, so I can put. So I can is this one?
Yeah.
So I can copy in there the IMARIS file, so then I can copy it back into my computer.
Okay.
And also the data set from you, so then I can share it with, if you don't mind, the developers to see how things, because with data sets how we can get to improve things.
No, that would be really good.
So and yeah, and then this one. And then if you don't mind, I copy everything and then we can delete it. And you said that there is some data set in this computer. So
Yeah,
far.
in Peter's folder, I think.
In the desktop files for no.
No, I don't know what he
Set.
installed.
I think this is the one we use for the
If you go up
tracking.
again, I think I might have just seen it.
Oh, how you go up in here? I don't know how to go
I
up.
don't know how to do that.
Out here, back. Okay. You.
Try that one.
So, click open, so we can show you a little bit how it looks like. Does it look like your image?
Yeah, that's what it is.
Yeah, okay, cool. Okay,
It'll be quite big.
it's quite big. Is there, oh, because you're interested, this is where you wanted to track.
So I'm mostly interested in the red cells that are moving, but the blood vessels are in there as well. And I want to keep separate the red cells, some are inside the blood vessels and some are outside, and I want to analyse them separately.
Okay, so is that alright if, for example, I just make it something more manageable? So
and if you want to crop your time as well.
Yeah, and let's say 40. Okay, so let me check that this has finished saving. So,
Actually,
oh yeah, it's saved.
Lisa,
Yes.
You take the third one down as well, because that's with membrane GFP, so that might be better.
Let's give them the worst case scenario. So, you know, it's okay. It's always, because things are never perfect.
Actually,
So
you get to collect the data with the one that's not as good in IMARIS, so that's why we tend to use it.
yes. So eject data back. Cool. Fantastic. Thank you. And IMARIS somewhere open.
If you go further.
Oh, here. Yeah. In the meantime, I can save this here. Okay, so if you don't see the display adjustment window, again, you can go to edit, show display, or just to click this shortcut and it will appear. So we can adjust a little bit the minimum and the maximum intensities to get the best contrast possible to see what we have. So we've got the vessel. Do we have
blue one you can get rid of.
Okay, there is nothing in there. And the green?
Green. It's not so important.
Okay. And then we have the red, which are our cells, right? Okay. Ooh, very low signal. So it's difficult to acquire something, or just no.
In a live animal through the skull.
Oh,
so
through, yes.
Because I'm not right at the vessels, I think the signal's not great.
Yeah, you are also deep in tissue and things like this. Okay. So I think maybe a little some deconvolution could help sharpen up the object. Here. This one and this one. Okay, so I think the best thing for the cells is definitely a spot to track them. So if what you want to do is not to track them when they are inside the vessel, is to use that mask. Yeah, and the best thing to do the mask is to segment the vessel. So here you can do it automatically. So we follow the wizard. Smoothing, normally it could be 10% or of the diameter of your vessel, or if you have also these bits here with a smaller diameter, so I will take the smaller diameter. So for example, like this. So let's say 11 microns, so a smoothing of 1.1 is good. And then we just have to pick up the vessel. Yeah, some vessels may appear a little bit like half pieces if the labeling is not complete. Now we make sure the surface is good for all the frames.
Is this when you use the clipping plane again to judge
You
whether
could,
over or underestimated?
yeah, you could also use the clipping plane if that helps you to estimate that threshold. Obviously, it's going to be always a little bit of a compromise because you will need to decrease that threshold in order to catch up, in order to segment these lower intensity areas from your vessel. And sometimes when you lower it, that means that maybe these areas can be a little bit larger inside, yeah. Maybe we can exclude this tiny object.
So I think I've tried to do it before and then I didn't know what all these dots meant.
Yes, these dots, because what happens now is because the computer is saying, oh, the mesh is too big, too many surfaces. And it may think that the computer graphic card may not be able to handle it or may take maybe less interactive, so suddenly it shows you the center point. So in settings you can come back to surface, and then it's when it tells you, oh, you have a lot of triangles for the surface. And if you display the surface, the software may be a little bit interactive, and the graphic card memory can overflow. Do you want to continue? Oh, okay, yes, just to show. So that's what is happening, and therefore what it's showing is just the center of mass of the vessel. You see, for example, now here, because the signal is being lost, here it's segmented in a nice way by here we have half a vessel. So I come back to create. If we want to stop that, so when you go back, what happens is that you have to go to lower intensity values, and which means that you know, maybe here it's been a little bit wider than what it could be. So it's just a little bit of a compromise. Also, what it can help here, if I step back again, is to use a little bit of a bigger smoothing to have more of a chunky. Well, maybe 2 is a bit big, I don't know, or 1.5. So we don't need to have so much detail in the surface. So it looks a bit more complete. So, okay, so this is good. Still these two, for example, there's hardly no signal there, so if I go to blend, so we cannot really join them because the signal is lost. So it's a little bit of a compromise. So okay, so we can go next. Okay. Thank you very much. And then we have again those dots, which is just the center of mass. Those dots there. Which is just the center of mass of the vessel. Good. So here, very easy tracking. I don't know, doesn't really matter. We can choose a small distance. Let's say just 10 microns. Doesn't really matter because it's a whole structure, so hopefully it won't do anything strange, I think. Still have okay, so I don't know what these tracks are in here. Doesn't matter. The tracking here anyway is not important, so tracking here is not important. What is important is that we have that surface over time. Oh, because it was this bit was appearing and disappearing. Okay. Because then this is what we're going to use as surface, excuse me, as a mask. So we can mask all properties, and in this case we want to mask the red channel. So we choose the red channel, duplicate channel, and we set voxels inside the vessel to 0. Okay. So we are left with red cells that are only outside the vessel. And we say apply to all time points. Yes, okay. Okay, so now this creates a new channel, which is the red channel that hopefully only have those vessels, those cells that run out of the vessel. So maybe what we can do also to differentiate them, maybe I just put this one in yellow or something like this so we can see it. And differentiate one from another. Well, I mean, the ones that are outside will be, actually we can make it, they will be also yellow, but we can make it green and we can see green and yellow, if it makes sense.
They're the ones inside.
So now the ones inside are only green, but the ones outside they will be green and yellow because they will have green.
Alright. Okay.
Does it make sense? So yes, we can see both at the same time. Or maybe we can put NIP again to see if that helps. So yellow, that means that they are outside.
Yeah.
And green, that are inside. Yep. So now what we need to do is just to track these cells outside. So now it's a easy tracking. So we use a spot. I guess you are not interested in the signal, in the shape of the cell, because
not really.
Because the signal is also quite poor. Yeah. So yeah. I don't think you will get a good quantitation of the shape, because it's just the signal is poor, and also you have the distortion instead, so maybe it's not going to be very meaningful for you. So we can use a spot. So again, for the mask channel that only has the cells outside, and we need to know the diameter in XY. So I go to slides, and okay, maybe here I start seeing some cells around 5 microns, 7 microns, maybe this one here, 7 microns. Okay, let's try 7 and see how the detection works. Okay, so now we are missing these ones here, which are real cells, right? Yeah. And what is happening here? Okay, I know what is happening here now. This is because the cell is very distorted inside. So what happened is, because this is much bigger than a 7 micron spot, probably 14 microns or more, trying to fit 2 cells there and 2 cells there. So we're going to correct for that. So we step back, and we use also this option, detect ellipsoids. So now the set will have an X shape, and there will not be 2 cells in there. Normally we can try with double the size, so that would work. Otherwise, in a slice, we can also measure that set distortion. So now we have X, and we still have 2 cells here. Is that really 2 cells? 1 cell? What do you reckon? But it could be that there are 2 cells together.
Did we see the next frame and or the one
Yes.
before it?
Let's see. So that's the previous frame. And maybe we can hide. This could be like 2 cells. And then we got that one there, and at the next one, so it's coming from the top. No, from the bottom. That could be a false one. This one. Oh, very strange. We can make the X shape a little bit longer, I think, to avoid this. So let's say 18 microns. I guess it's difficult to, because let me see the slide. What is the step size? Edit, image properties. Okay, the step size is 2 microns. So if we are looking, so this I don't know if it's possible to acquire more set steps, or is this challenging in the image? Because probably your cells are also losing resolution in set because the set step is too large.
Okay.
Because it's more, for example, if your cells are maybe around 7, they look like 7 microns in XY. So I don't know, maybe a step size of 2 microns is a little bit too large. That's why it looks a little bit like now we have the cell, now it disappears.
Yeah.
I don't know. So I know, I understand sometimes the limitations of light imaging. Sometimes it's not easy. That's why I'm asking before anything, if it's possible to get a bit more set. Yes, because we start I'm trying to estimate a little bit as best as possible the size of the cells. These may be better parameters, I think. I don't know if that is a real positive or not. I don't know, because what is happening here is that May is starting to lose because these are real cells, right? This one. Yes, it's a little bit of a compromise to try to choose the right settings. So let's see, because the signal is a little bit poor, so we'll see. So not so as straightforward as that. Hopefully inside there should be, yes, there is one there. Okay, I think this can be a good detection. Okay, so here this is the chance of maybe if we are missing something, maybe adding some of the cells. For example, if we are missing it there, so maybe we can add a cell there. Come back again to me. So the object here. And this one here. Okay, something like this. Yeah, something like this. And now we need, so now I finished the detection. We can choose, autoregressive motion and the maximum distance. So again, let's try to see from my frame here is 10 microns. So just to see how the cells move. If more than 10 microns, less than 10 microns, just to have a bit of an idea. Now I'm looking, for example, this one here, it may have a step of more than 10 microns. So, I don't know, I'm just going to choose something like 15. And in case they appear from one frame and they come back at the next one, things like this, I think I'm going to allow just for 2 frames for an object to disappear, because there is no a lot of resolution in the signal. Okay, so now we have some tracks. Okay, so seem to be okay. Oh, maybe there is something happening in here. We can try to see what's happening and if we need to join those 2 tracks, but we can do that at the end. So now we can investigate what is happening there. Oh, because it's another object that comes from Z, from different planes, so it's okay. Okay, so now we have the tracks. Okay, so let's play the movie and see how they look like. Maybe we can put again the blend mode, and we can make the channel a little bit transparent. And then from the statistics, you can get all the information of the movement in detail.
And this is what I wanted to know, whether I could get the X, Y and Z coordinate at each time point for each cell.
Yeah.
Yeah, how would I do that?
Yeah, you can. So you need to look at position.
Okay.
And position, it will give you the position X, Y and Z coordinates over time. So if you play the movie or if I change the frame, the position change. See?
So when you export it, will it give you at each time then?
Yes, it will. You will export it for all time frames.
By pressing
And
this floppy disk.
so if, for example, if you want just this value, the single one will export only this. If you export the multiples, it will export position, but it also will export all this long list of other statistical values.
If I do just a single floppy disk, will it only give me the position at this time frame that we're looking at?
No, for all time frames, for all the objects, but just the position statistic.
Okay.
Yeah. And yeah. Is that what you needed to know? Do you need to know something else?
Can put all these trackers together, join together into like X, Y.
Yeah, like translate.
Yeah.
here the function is not activated because it still needs, basically what you do, you use this function translate tracks.
Yeah, okay.
But here it just needs installing the MATLAB compiler to activate this function.
So in the sports function, no?
Yeah, yes, in here in the last, doesn't matter if it's a sports or surfaces, okay. So you go to the last tab and you click in translate tracks. So maybe I can show you my computer where that option is available. So it's also available in this license, it's just that they recently acquired the license, so they haven't activated yet that function.
We don't have that. So we don't have that XT, but that's Sarah's.
So you have this, you have all the tracks like this.
Mm-hmm.
So now what I need to do, I select one track.
Yeah.
And I click translate tracks.
Yeah.
So this starts this MATLAB program. So now I remove the signal so it doesn't get confusing. So when I play the movie, you can see all the tracks starting from the same point, moving to all the different directions instead. You can also put the display.
It's just a 2D X, Y.
This is.
I don't need the.
Well, if you if you have only a 2D image, then that plot will be 2D. The reason why it's 3D is because here the cells are also moving in Z and we have a volume.
I usually consider this one.
Yeah, I was going to ask you this. If I retake these tracks now, and in Vantage, plot that as displacement X versus displacement Y, we get a similar plot. Is that the same thing we're looking at?
Not really, because these are translated. So the positions are recalculated because they all start from the same position. So the coordinates, the X, Y, and Z coordinates are different from this because they are all relative to the track that you click on versus this. So here, yes, you can go and say build X, Y, or maybe just an X, Y, and then you can have the X position and the Y position. But it's not relative to...
It was the tracks that we followed rather than the dots. Was it the scatter?
Yes, scatter.
Under the scatter plot?
Yes.
And then we reprogrammed
position,
X, position.
Positioning.
But it was displacement.
Displacement.
Displacement. Okay,
displacement X and displacement Y.
No, this is the area diameter is the intensity. No. Is for the track.
Yes.
And for the track, you choose track displacement length.
No, it's displacement X versus displacement Y.
Yeah. Okay, let me try something, because sometimes what happens is that in the statistics it may not have that activated.
Right.
So if you go to the configure list, displacement X, so she didn't have it activated at all. Or square displacement, but okay, select it also just in case. Okay, so now the statistics are calculated, so we can come back to Vantage, and so we can choose spot and this displacement X and displacement Y.
Okay, take off the grid, just X,
and
Y.
Now we take let's finish. So if we don't want the grid, little hot.
Yeah. Is that essentially that recreated, or have we got something different?
Good question. Yeah, it may be. Yes, it is. Okay, I see. The difference is that here you're looking at position. So let's say now the particle is a position x5, the next frame is a position x15. Here it shows you now that the spot E has moved 10 micron. That's what the displacement is.
Okay.
Yeah, so that's the difference. These are like the way we look at it like this. The coordinates have been recalculated. So, for example, if you look at the statistics and you look at the position, so that position is going to be different than if you look at the original spot and you look at the position. The displacement will be still the same, right? Because they still move that distance. So, yeah.
It's a graphical representation though. They're the same, it's just how you get there is different. Am I right?
No, it's a different type of plot. Because for this, of course, you don't need to translate tracks because everything starts from 0, 0, coordinates at 0, 0. These coordinates can be whatever coordinates are related to your microscope space and stuff.
Are they two plots from the same data?
No, they are completely different.
Okay.
So let's try. Let's have a maybe we can do a silly test. So if I go here to Vantage.
Not on our we don't have that's there.
Okay, let me make first. I will make this spot red. So I just make the normal spot green and the translated spot red, and I try to plot the same coordinates, the same stuff for both, and see if the plot looks the same or not, if it makes sense. So, scatter. Just to make it simple, I just choose X, Y, and we choose displacement X and displacement Y. Yes, it's the same.
Cool.
Because here now you can see that it's the same. And finish. And now, for example, the spot 1, make it red. Yes, it's the same.
Okay.
Ah, see, I also learned something new.
Cool. Save us some money there.
Yeah. So I also learned something new. There you go.
Okay, cool. So
Yeah,
PT just walked out just at the point that we said we can do it.
Yeah.
Yeah. Okay. Brilliant.
Cool.
That's good.
Can I ask you about my data? I know the signal's not great. Is there any way that I can make it look better? Say I wanted to show someone in a presentation or make a picture for a poster.
You could. Because I don't know of how because when you do in vivo, especially through skull, and I think it's very challenging. So, do you use multiphoton?
That was
multiphoton. Okay, yeah, that's good. Okay, so you could try to decompose the data, so you reduce the noise, and the quality of your image will be a little bit better. Also, sometimes what happens is that when you do the convolution, people say, "Oh, that's the intensity is much lower." Is because imagine now you have a pixel with intensity 10, but maybe 5 intensity units are just noise.
Yeah.
That's why when you deconvolve, you just see only 5 intensity units, and it makes look that your intensity has lower signal. It's not that, it's that you have cut the noise, you have subtracted the noise. But then your image will, the quality of your image will be much better. So you could try to decompose the data set. And also, I don't know if possible, maybe the set a bit smaller, if possible. I know it's challenging. Cool.
Do it all in isosafety.
This is it. If I show it, should I put a surface on it?
I mean, you could. The reason of using a spot is because it's a better detection. You can, of course, try to use a surface and try to do the analysis of the red channel using surfaces and see what happens. Maybe we can also use this background subtraction. So we said the cells had a diameter of around 7 microns, and see. Do we say 7 or I'm imagining it? I can't remember. Yes, 6. Okay, 6, 7. Okay, let's say 6 just in case. And see if the background subtraction detects the objects a bit better. Maybe. Maybe actually can be a bit better, because maybe can be a bit better actually. And then what we can do, we can get rid of that little debris. So here in the filter, a filter to do with the number of box cells is equivalent to have a filter for volume, and we can exclude the small objects. I don't know if that is a real cell or not. Yeah, maybe something like this. And then same settings as before, so I don't remember what I used, but I can go here and I use autoregressive, maximum distance 15 microns, gap size 2, okay? So 15 microns, gap size of 2. Now maybe we can get, I don't know if you want, maybe this is a little, could be debris or something like this, I don't know. Let's see where the signal comes up. Yeah, probably this is just not really a cell. This tries to come into the field of view, but it doesn't. So maybe we can exclude I'm very short. Okay, let's leave it there. Because this is a filter to exclude for track duration. So if they last for just a very few time frames, like this, probably this is not going to give you good statistics. So you can exclude it. Okay. There you go.
If you did an animation, you start with the real data and then you you were fudging it completely.
Yeah. What's happening at the end of the movie? Not those music? Okay. So now, see the difference, for example, is that now starts taking, probably this is a leftover, I don't know, signal of the surface or whatever, so the surface is the joint a little bit there, while the spot may have hit. If I put the spot. Now the spot is not quantifying it there, okay. Yeah, maybe surface is alright. It's okay. Yeah. Yes. Cool. So, do you want me to save this? So you have the settings there. I'll save it in the desktop.
Yeah, I'll just something else tomorrow.
Yes. Okay, cool.
What time do you have to leave?
I think my train is at good 6:30. Okay, so I'll go with plenty of time.
Just a short
Still I
question.
can.
So if I will need some help with the software, should I contact directly you or
EU support.
you?
Yes, that's the best. I mean, you can contact me, but sometimes if I'm very busy, I may send the question back to EU support or.
Okay, so I will wait for you to come back.
Yes.
With this, but perhaps meanwhile I will also try to play.
Absolutely, yes. Yeah,
Okay,
excellent.
then EU support.
Yes.
Okay, I need to go. Thank you.
Yeah, you're welcome.
All right.
Thank you. Question?
Yes.
Yes, of course. So,
Shouldn't take long, it's just measuring distances between dots.
okay.
Trying to get it alternating.
Oh, we shouldn't get long. You never know.
It's a dangerous thing to say.
Yes, yes.
Well, I nearly got there. The first time I used measurement probe seemed to work.
Okay.
I was basing it on the intensity from one dot to the next. I measured distance. But then the second round, it didn't seem to work. I couldn't figure out what I did.
Okay.
It might be better. I was just using gauged Gaussian filters on them. I think it might be better to decompose it. But just if you
Okay,
just
what
figure out how
happened?
to use it.
Which data set?
For IMARIS demonstration. So they're similar stuff, but just at different resolutions. So if you try the 60 or 40.
Oh, this one is 60, okay. Close my IMARIS again.
So the main question was, like, most people,
Mm-hmm.
for these things to be considered still applied, should be less than 350 nanometers. I wonder whether you could just set it to say how many cells in all this, or how many of these dots are less than 350 nanometers,
Yeah.
and just get a big, like, table or whatever.
Why on that?
So some of them at OIF, they've put some OIBs on because I think this will struggle. But I know the one in Nancy's lab doesn't like OIF tiles. Times 40, that's OIB.
So,
Unless you know if there's some OIF, but I just have to
oh
change
yeah,
them all
we
on.
should be able to open Olympus file.
Yeah,
I think it's because we should.
that's just a raw file.
Yeah, but we should. It's not accompanied by any other, because sometimes the file has like, I don't know if this is the case for iOS, but for example, if you have this sort of format, I see. This type of format,
Yeah.
you need this and this file. But this is not in order to open it,
Yeah.
because one is the metadata, another is the image, because we should be able to open these IOF files for sure.
Yeah. The thing will be.
And it doesn't.
You can try with the time for the ID one if you want.
Because normally Olympus, we collaborate a lot with Olympus, that's why I'm saying. Let's see, so...
My passport.
Which one you said?
Times 40, so ID is bottom one. Yeah.
This one. Okay. Okay, I will save it from here then into the desktop.
You've got 2 bands.
Mm-hmm.
And in the green you should see a small amount of red.
Yes, we have these 2 bands.
Yeah, so normally you can see some reds. So you can see here where some of the red turns up. So we want to measure the distance of the red and the green in this back band.
Ah, okay. I think it's better because this function is not activated here, because there is this IMARIS XT function that is find distances between spots, colocalized spots, and that's the one that actually tells you how many green, for example, how many of the greens there are within 0.3 microns to a red.
Right.
Yeah.
What's that called?
So if you don't mind, I close this.
Cause I was just googling it, and the Measurement Pro looked like the best, but it may not be.
Yeah, it can be, but for manual, you have to do it manually. But we can do it automatically. So we have to do it in my computer.
So we're finished with that one then, really?
Yes.
I'll shut that down.
Do you want
Take
to
it away.
no? So